This video is the first in a series for Earth 125 Statistics and Data Analysis in the Geosciences class at UC Santa Cruz. And first, we'll discuss one very important way of describing numeric data called the central tendency. This is just the middle or the center of a data set, often called the average, and it's very important when we later on will try to compare differences among groups. So any set of data that you have is going to contain many individual observations. So it's important to have some kind of value to summarize the characteristics of that data. And most statistical tests, like the ones we'll discuss throughout this class, are designed to compare differences in these summary values. The two most important ways of summarizing data are the central tendency, which is the typical or average value of data in a data set, and the focus of this video. And the other is the dispersion, which is the variability in values in a data set, and the focus of the next video in this series. So virtually all of the statistical methods that we'll cover later on are intended to compare data between two or more groups. For example, we might want to compare the size of sand in a river to the size of sand on a beach. Of course, we're not going to measure every single sand grain on the beach, so what we really do is to collect a smaller sample and use that to estimate and compare characteristics of the population. So the population is this sort of infinitely large universe of sand grains or whatever, and the sample is a small set that we've taken that we hope is representative. So we'll come back to this idea later on when we discuss statistical hypothesis testing, but first of all, how can we, given some measurements in a sample, quantify the central tendency of that data set? So the most important and most common measure of central tendency is the mean, technically the arithmetic mean, which is given by this symbol x bar. So x bar is the mean of our sample data. And so the mean is simply the sum of all observations in the sample, which is this Greek letter sigma means sum, and then we divide that by the number of observations, or the number of things that we measured in the sample, in this case, and typically given by n. So you might be familiar with this measure under its common name, or the average. This is what you often think of when you think of the average of something, but it's technically the mean, and as I said, specifically the arithmetic mean, because there's actually other types of means. And so remember that that we're using this smaller representative sample to estimate characteristics of this large population, which is sort of infinitely big and we can never actually assess. So this x bar is the sample mean, and we're using it as an estimate of the population mean, which is given the Greek letter mu. So the other commonly used measure of central tendency is the median. And as far as I know, there's no sort of standard symbol for this. The median is just the middle value in the series of numbers in the data set. So basically, if you take your numbers, the measurements that you made, and put them in order from smallest to largest, the median will be the middle one. So in this example here, the median is 6. There are two numbers smaller than it and two numbers larger than it, so it's the middle number. If you have an even number of measurements, there is no middle number. So in that case, the median is just the arithmetic mean, the mean which we discussed in the previous slide, of the two middle numbers. So in this case, there's an even number of measurements, so there's no middle number. So the mean is just the average, so the median is just the average or the mean of 6 and 8. So the median in this case is 7. And so again, as we go through, remember that this is the sample median, and we're using it as an estimate of the true population median. So the big question then is, when should you use the mean, and when should you use the median? So let's consider a case where your data follow this symmetrical distribution. So this is a histogram, this graph here, and it basically just divides your measurements into bins or groups and then plots the number of values found within each bin. So in this case, the mean and the median are basically the same thing. So in this case, you might as well use the mean as your description of central tendency. If you have a symmetrical distribution with a peak in the middle and both sides are around the same size, the mean is the best measure of central tendency. It's the most precise. It uses the most information. However, if your data are very skewed, and skewed means that the peak is on one side and there's like a long tail on the other, the mean and the median are not going to be at the same place. And in fact, the mean is going to be affected much more strongly by these rare outlying points in the long tail. So if the distribution is skewed, the median is the best distribution of central tendency. And so basically, you should use mean if your distribution is symmetrical, and you should use median if your distribution is very skewed. And in the middle is going to be some judgment call where you're going to have to decide. So in R, it's very easy to calculate a central tendency because there are built-in functions to do specifically this. So you'll need a group of numbers, which is called a numeric vector in R, as the input. And so I'm going to denote that here as x. I'll just use x as our string of numbers. And so the function to calculate the mean is, perhaps not surprisingly, called the mean. And so the output will be displayed to the screen, or it can be assigned to a variable. So you just do mean brackets x, and that will calculate the mean of that numeric vector x. So there's one note to be aware of. If there are any missing values in your data, so if your input has measurements, but maybe a couple of them don't have a measurement, so it's missing, R will treat those as NA, or not applicable, and the output of the function mean will also be NA. So in that case, you want This video continues the discussion of descriptive measurements that can summarize numeric data. We previously talked about central tendency, and now we're going to talk about measures that can describe the dispersion, or the variability of measurements within a sample. So statistical samples contain many individual observations or measurements, and so therefore it's important to have some kind of value that can summarize the characteristics of that complex data. You learned in the previous video about measures of central tendency, the average, and this video introduces measures of dispersion or variability in the values of a data or sample. We'll move on to statistical hypothesis testing of those measures later on. So dispersion is just a technical term for variability, describing how spread out the data points are around the center of the data, with the center usually being measured by the mean. The simplest way to measure dispersion is just to calculate the distance from each point to the mean. So you just subtract the mean from every point. However, there's a problem with this. Because points smaller than the mean will have a negative difference, and points larger than the mean will have a positive difference, they're going to tend to cancel each other out. It's not a great measure of dispersion then. So what we do is, instead of just using the actual distance, we use the squared distance from every point to the mean. So you subtract the mean from every point and then square that number. And this will convert those negative distances into positive numbers. These are then summed up or all added together to give a measure called the sum of squares. Just the sum of the squared distances from each point to the mean. This is an extremely widespread and important way of measuring dispersion, around the mean at least, and it'll come back again. We'll see it later on. So as a short aside, you might be wondering why the values are squared. Why don't we just use the absolute value of the distances? It's partly convention, but the sum of squares does have some mathematical benefits. For example, it's mathematically easier to find a value that minimizes the sum of squares rather than finding the minimum of the absolute value. There's other things as well, but that's sort of one of the reasons. But the sum of squares on its own isn't used to quantify dispersion that often because its magnitude varies with sample size. You might imagine the sum of squares for 1,000 data points, you're adding up 1,000 numbers, is almost certainly going to be larger than the sum of squares for just 10 data points, you're adding together 10 distances. So dispersion is instead measured often as something called variance. So the sample variance is just given the symbol s squared. Variance is the sum of squares, that we saw on the previous slide, divided by n minus 1, where n is the sample size, the number of measurements in your sample, the number of observations, for example. So why n minus 1? Why can't we divide just by n? Why don't we just divide by the sample size? Well, this is related to something called the degrees of freedom, and that might be easiest to illustrate with an example. So let's consider this small sample here of 5 observations. You know the first values are 4, 6, 6, and 4. And so what could the fifth value be? Well, it could be anything. I mean, it's probably be something like 4 or 6 if you're extrapolating, but it could be 4.5, 4.672. It could be 15. We don't even know what it is. There's no constraints on that fifth value. It couldn't be anything at all. But now imagine the same data set, 4, 6, 6, and 4, but now we know that the mean of the sample, x bar, is 5. So if the first 4 values are 4, 6, 6, and 4, the fifth value must be 5. If the mean is 5, the fifth value can only be 5. So in that case, if we know n minus 1 values and the mean, the final value has no freedom to vary. So we have 4 degrees of freedom in this example. We're essentially using one of them to calculate our sample mean in the equation for variance. So basically, n minus 1 is often used in these things where one of the degrees of freedom is used to calculate the mean. So this gives us what's called the unbiased sample variance. The n minus 1 is the unbiased estimator as opposed to just using n. So sample variance is calculated as the sum of squares divided by n minus 1 because we have n minus 1 degrees of freedom, having used one of them to estimate the sample mean from the data itself. So the sample variance s squared is used as an unbiased estimate of the population variance, which is given sigma squared. And so unbiased just means that there isn't a tendency for it to be either low or high. It doesn't mean that it's really precise, but it means that it's not going to be typically lower or typically higher. It could be lower, it could be higher, but we don't really know. So because the sum of squares because we're using the sum of squares, variance is measured in the original units squared. So if we're measuring the grain size of sand grains, our variance will be in millimeters squared, for example. That's kind of an awkward unit to use. And so for that reason, if we want to describe the dispersion when we're writing a sentence or in a table in a paper, it's more common to report the standard deviation S. The sample standard deviation is S, so it's just the square root of the sample variance. And this has the same units as the original data. If our data are sizes, our standard deviation will be in millimeters, or whatever unit we measured. So remember, in statistics, we're using a small, hopefully representative sample to estimate characteristics of this large population. And so the sample standard deviation S is going to be an estimate of the population standard deviation, which is given as sigma. So variance and standard deviation are quite commonly used to compare dispersion between samples, but there is one potential complication that comes up, at least in some cases. Because these deviations are measured from the mean, the magnitude of those deviations, and therefore the size of the variance or the size of the standard deviations, will tend to be larger when the mean is larger. So variance has some relationship to mean, and that can be a problem, and it's certainly in certain cases, which I'll illustrate next. So we can avoid that problem. We can avoid the fact that the variance has some relation to the mean by calculating something called the coefficient of variation, which is just the standard deviation S, our sample standard deviation, divided by our sample mean x bar. So again, remember that we're always using a sample to estimate parameters of this larger population. So our sample coefficient of variation, CV with a little hat on it, is an estimate of the population coefficient of variation. You don't really see coefficient of variation that often because it's only useful in very specific circumstances. But it can be useful for comparing dispersion if the two measurements have very different units or if their means are very different. Remember that variance has some relation to the mean itself. It's important to note that just because the means are different, you don't necessarily want to use coefficient of variation. You really want to use it if that difference in means is actually important, as opposed to just being sort of random noise in your data. So it's important to note that the coefficient of variation is only meaningful if all of your measurements are positive numbers. If you have some negative numbers, it's not going to make any sense. And you also should be warned that the calculated number is going to be quite sensitive to changes in the data if the mean is close to 0. Because we're dividing by the sample mean, if that's a very small number, small changes, if the mean goes from 0.001 to 0.002, your coefficient of variation will change a lot, even for very tiny differences in the mean. So you may still be wondering, when should I use the coefficient of variation? Well, here's an example. Let's say we want to know whether earthquakes, like large earthquakes, occur more regularly in Japan or in Cascadia, the subduction zone along western North America. So we want to know, is the time between earthquakes more regular in Japan or in North America? So I've just made up some numbers here, and it tells you that the mean time between earthquakes in Japan is 100 years, and it's 400 years in Cascadia. The standard deviation of the time between earthquakes is 20 years in Japan and 40 years in North America in this made-up data set here. So if we just looked at standard deviation, we'd say that, well, Japan is much more regular. The earthquake timing, the time between earthquakes is much more regular than it is North America, because the standard deviation is only 20 years and not 40 years. But if we calculate the coefficient of variation, standard deviation divided by mean, we find that Japan is 0.2, 20 divided by 100, and Cascadia is 0.1. So we'd actually make the opposite conclusion, that the earthquake timing is actually more variable in Japan, the time between earthquakes. So this is an example where the mean differs, and we might want to use coefficient of variation, although you've got to be a little careful sometimes. More commonly, you want to use coefficient of variation when you are comparing things measured in different units. So for example, if you want to know, is pH more variable than temperature, or is temperature more variable than pH if we measure it in a bunch of different lakes? Those are measured in different units. Temperature is in degrees Celsius, pH is in pH units, and so therefore it really wouldn't make sense to compare the actual raw standard deviations, which are measured in degrees Celsius or pH units. If we divide by the mean, we are dividing degrees Celsius by degrees Celsius, and so we get a non-dimensional measure of comparing variability. So R has built-in functions to calculate both variance, VAR, and standard deviation, SD. Like the mean and median functions from the previous video, these both require a single numeric vector, a single set of numbers, as the input. Like I mentioned with the mean, these both treat NA values, missing data, as NA. And so you'll run into this problem where if there is missing values, the result of the function will also be NA. So you might want to remove those NA values using this NA.rm equals true option that's built into either function. So I don't know of a built-in function to do coefficient of variation in the base version of R at least, but it's not really necessary. It's just standard deviation divided by mean. You know both those functions, so you can calculate it pretty easily. So the output of this and any function will be displayed to the screen if you just type this, or you can assign it and store it as a variable. This video builds upon our previous discussion of central tendency, mean, and median to introduce the descriptive ways that you can use to summarize numeric data, especially those that discuss the dispersion or the variability of values in that data set. So, as we saw before, statistical samples contain many individual observations or values, and it's important, therefore, to have some kind of way to summarize the characteristics of that data set. And so you learned in the previous video about measures of the central tendency or the average, and this video introduces measures of dispersion or the variability of values in the data. And we'll move on later on to discussing ways that you can use statistical hypothesis tests to distinguish between dispersion in different samples. But for now, we'll just talk about the measures themselves. So dispersion is just a technical term for variability, which describes how spread out the data points are around the center of the data, with the center usually being measured by the mean. So the simplest way to measure dispersion is just to calculate the distance from each point to the mean. Because points that are smaller than the mean will have a negative distance, they'll tend to cancel out the points that are larger than the mean. So to get around that, we square those distances. This will convert the negative distances into positive numbers. This is then added up to give us something called the sum of squares. And the sum of squares is an extremely widespread way of measuring dispersion. You'll definitely see it later on in this course as well. So just as an aside, you might be wondering why the values are squared. Why don't we just take the absolute value, which would also help get rid of those negative numbers? Well, it's partly just convention, but also the sum of squares and the squaring of the values does have some benefits. It's mathematically easier to find the value that minimizes that, for example. But anyhow, the sum of squares isn't used on its own to quantify dispersion because its value will vary with the sample size. So the sum of squares for 1,000 data points will obviously be larger than the sum of squares for just one. And as I said, we'll see this later on. It comes back again and again in different statistical tests. So dispersion is instead measured by something called the variance, which is given the symbol s squared for the sample variance. And we just divide the sum of squares by n minus 1, where n is the number of values in the sample, or the sample size, essentially. So why n minus 1? Why not divide just by the sample size n? Well, this is related to something called degrees of freedom, which is probably easiest to illustrate with an example. So let's consider a small sample of just 5 values. If you know the first values are 4 and 6 and 6 and 4, what could the fifth value be? Well, it could be anything. You might guess it's something but like 4 or 6, but it could be 15 or 4.5. We have really no idea. There's no constraints on what this can be. But let's imagine the similar situation where we have the same data set, 4, 6, 6, and 4, but now we know that the average, or the mean, is 5. So if these first 4 values are 4, 6, 6, and 4, in this case the final value could only be 5. Because given that the mean is 5, the average of those things has to be 5. So in this case, if we know n minus 1, if we know the first 4, and we know the mean, this final value has no freedom to vary. It has no degrees of freedom. It must be one thing. It must be 5. So this is essentially why, if you look at the formula for variance, the mean is in there. So we're essentially using one of the degrees of freedom to calculate the mean. So variance is calculated as the sum of squares divided by n minus 1, because we only have n minus 1 degrees of freedom. We've used one of them to estimate the sample mean from the data itself. And so the sample variance, s squared, is an unbiased estimate of the population variance, which is sigma squared. And unbiased just means that there's no tendency, it's not going to be high or low. It's not going to be perfect, but it's not going to be biased or deliberately in a higher direction or a smaller direction from the population value. So because the sum of squares and variance, therefore, is measured in the original data units squared, it's kind of awkward. For that reason, if we want to describe dispersion in writing, if we want to say the variability of this data set is something, it's more common to report something called the standard deviation, which is just the square root of the variance. And so because we take the square root, standard deviation is the same units as the original data. If we've measured rock chemistry in parts per million, if we have the size of something in millimeters, the standard deviation will also be in parts per million or in millimeters. And so remember, this is the sample standard deviation, or S, and it's the estimate of the population standard deviation. Right? Statistics is always trying to estimate a population parameter from the sample that we have. So you may have noticed that the formula for variance, and also therefore for standard deviation, uses the mean as one of its inputs. And you've also learned that the mean isn't a great measure of the central tendency when the data are strongly skewed. So as a result, variance and standard deviation aren't great measures of dispersion in cases where the data is strongly skewed. So instead, there's something else that you can use called the interquartile range. So any data set can be divided into 4 quartiles. The lower 25%, the second 25%, the third 25%, and the upper 25%. And so the interquartile range is just the range spanned by the middle 50% of those data points, which is the dark green shading in this histogram here. So it extends from the lower quartile, 25% of data points are smaller than that, to the upper quartile where 25% are larger. So in this example, the lower quartile is between 0 and 17.7 or so. Upper quartile is about 59 to 400-ish. So the interquartile range is about 58.7 minus 17.7, or 41 parts per million in this case. So sometimes you see interquartile range given as the actual range, like 17.68 to 58.69. Sometimes you see it just as a single number, which is the difference between those two. You sometimes see those interchangeably, but in R, and it'll give you, and if you want to report one value for dispersion, you want to report just a single number there. So one other thing, so even if the data does have a symmetrical distribution and variance is okay, there's still one additional complication with variance or standard deviations. And so because the deviations in our sum of squares is measured from the mean, the magnitude of those sum of squares, and therefore the variance of the deviation will tend to be larger when the mean itself is larger. This is a common relationship. So, if the mean is only 0.001, the standard deviation is going to be similarly small. But if the mean is 1,000,000, the standard deviation could be 1,000 or 10,000 or something like that. So if you want to compare variability in things where they're on very different scales, you use something else. And so this can be done by calculating something called the coefficient of variation, or CV. Which is just a standard deviation S divided by the mean, or this X bar. And these are the sample parameters. Remember, we're always using the sample parameters to estimate the population parameters. So this sample coefficient of variation is just the estimate of the population one. Coefficient of variation isn't as widely used as standard deviation, but as I said, it can be very useful for comparing dispersion or variability if the two measurements are in different units, or if the means are very different, and if that difference is important. So this is where you would use coefficient of variation. If the data types are different, let's say we want to compare, like, is pH more variable than carbon isotope composition? Well, they have different units and different scales, and so it doesn't make sense that they shouldn't have comparable standard deviations. It's also important to note that the coefficient of variation is only meaningful if all the data values are positive. So you can't use it if you have negative numbers. And also be warned that the calculated number is going to be very sensitive to change if the mean is close to 0. We're divided by very tiny numbers, and so the coefficient of variation can fluctuate a lot for very small changes in the mean if the mean is 0.001 or something like that. So here's an illustrated example of when you might want to use coefficient of variation. So say you want to know whether large earthquakes occur more regularly in Japan or in Cascadia in North America. So this is just made up numbers here, but it says that the mean time between earthquakes in Japan is 100 years, and it's 400 years in Cascadia. And the standard deviation of the time between earthquakes is 20 years in Japan and 40 years in Cascadia. So you had a long time series of earthquakes, and you measured the time between them, kind of the standard deviation of those times between earthquakes. So it looks like the Japan subduction zone is more regular, less variable, has a lower standard deviation, but also notice that the means are quite different. And so if that difference is important, which in this made-up data it is, we would then calculate the coefficient of variation instead. So standard deviation divided by mean. Japan is 0.20 divided by 100, or 0.2.
Cascadia is 40 divided by 400, or 0.1. So the conclusion is actually the opposite. Earthquake timing in Japan in this made-up data at least seems more variable than in Cascadia. So another example for using coefficient of variability could be if you want to compare the variability of pH levels and temperature in a bunch of different lakes. pH and temperature are measured in different units, and so it wouldn't make sense to compare standard deviations because those also have those same units. pH units versus degrees Celsius. And so the coefficient of variation is basically a non-dimensional method of comparing variability. So when you practice with the exercises, you'll get the chance to decide whether standard deviation or interquartile range is the appropriate or the most appropriate measure. You also get a chance to practice identifying situations where the coefficient of variation is a reasonable thing to use. And so these measures of dispersion are generally very important things to report when you give summaries of important data or important conclusions in written reports, when you're describing data, for your own research or for projects that you're working on. One major type of statistical inference is designed to compare two or more samples by proposing and testing something called a null hypothesis. This video will introduce some of the concepts necessary for choosing and setting up a statistical test, and the next video will describe how you interpret the results of a test, in particular one result called the p-value. So let's use a deliberately vague example for this purpose. We'll cover specific statistical tests over the next few weeks. So this vague example we'll use to illustrate the process. We'll just ask the question, is there a difference in grain size, let's say mean or median, doesn't really matter now, between sand from a river and sand from a beach? This is an example I've used in previous videos. So when choosing an appropriate statistical test, the first thing you got to determine is the type of data that you're working with. So there's two main types. Often you'll have what's called continuous data, where the variables can take any value. The range might be bounded, but the measurements can be any real number within that range. For example, temperature or density or calcium concentration are all examples of continuous data. Density is bounded, it can never be below 0, but it can take any positive value, 2 or 2.3 or 2.4172 or whatever. So there are tests that are designed to compare continuous variables between two or more groups, as well as tests designed to examine the relationship between two or more, continuous variables. So we'll talk about the specific tests in upcoming weeks, but for now it is important just to understand what continuous data is. So the other main type of data is called count data. So these are counts of items in categories, like the number of quartz grains in an area of rock, the number of species that survived in extinction, and so forth. Because they're counts, they must be positive values and they must be integers or whole numbers. You can't have a fraction of a species or half a quartz grain. So this data often comes in the form of a contingency table, which lists the counts of items in the categories. And we will come back to this type of data in a couple weeks. So once you've determined the type of data, and especially if you're dealing with continuous data, you often need to know the number of samples and the number of variables in order to choose the appropriate test. So most commonly you'll have a single variable, one parameter, one thing that you've measured that you're comparing between your samples. And so this is called univariate. There are tests designed specifically to compare two samples. So for example, comparing pH, which is one variable, between two lakes, two samples, two groups. Or calcium concentration, also one variable between two samples of granite. Or shell length, a single variable between two different species of clams. If there are more than two samples, if you have more than two groups that you've made measurements from, then you'll need to choose a different test. To be discussed later, in actuality, all these tests are particular cases of a more general method, but we're not going to get into that. So for example, you might have pH measured in 5 different lakes. pH is one variable, so it's univariate, but you have 5 samples, 5 different lakes. You might have calcium in 4 granites, shell length in 10 species. So basically the difference is whether you have just 2 samples or more than 2 samples. So less commonly, you might want to compare more than one measured parameter at the same time. Doesn't matter how many there are as long as there's more than one. And this is called multivariate data. So it means multiple variables, multiple things you've measured. Like before, there are different tests if you want to compare just two samples or more than two samples. So example might be that you want to compare both pH and temperature in two lakes. Or you want to compare all of the major chemical elements measured in 4 different samples of granite. So finally, you should determine whether your data are normally distributed or not. The previous video on standard error briefly introduced the normal distribution, but basically the key thing to note is that, and you've also dealt with this when you have looked at mean and median, is if the distribution of the values of the measurements is symmetrical, sort of has a peak in the middle with tails of about equal size, and is unimodal, a single peak near the center, you can run something called a parametric test, which assumes and requires that your data are normally distributed. If your data are not normally distributed, and especially if the data are skewed, which means not symmetrical, the peak is not in the middle, as shown here, you should run a non-parametric test. And again, we will discuss specific examples of these sort of tests in future videos. So this type of statistics, this null hypothesis significance testing, is built around attempting to reject a null hypothesis. So the first step is to formulate that null hypothesis. It's often referred to as H naught, this H sub 0. So a good null hypothesis is a statement that must have a single unique outcome that can be tested. So in our example here, we want to rephrase the question into a hypothesis statement. So our question is there a difference in the grain size? But we want to make that into a statement that only has a single possible outcome that we can test and potentially reject. So the most common choice of a null hypothesis is that there is no difference between the groups. So for example, we can say grain size is equal in river and beach sand. That's a good null hypothesis because it has a unique outcome, that there's no difference, the difference is 0, and it can be tested. In theory, you could choose any unique outcome. You could say river sand grain size is exactly twice as large as beach sand grain size, but this no difference null hypothesis is traditional. A null hypothesis, for example, that river sand is bigger than beach sand, even if that's what you think is true, isn't a good null hypothesis because there are infinite number of ways in which river sand could be bigger. It could be twice as big, 3 times as big, 0.5 times as big. So it's not easy to test and reject. You want a null hypothesis that has only one outcome, and traditionally that outcome is that there is no difference. You can also explicitly state an alternative hypothesis. Normally your alternative hypothesis suggests that there is some difference between the two groups, in this example at least, but you can specifically test if one group's mean is greater than the other or less than the other. So this is an extremely important warning, however. You can't choose your alternative hypothesis based on the data. Just because you look at your measurements and see that river sand is bigger, that doesn't mean that you can choose the alternative hypothesis that river sand is bigger. So from the photo, it's fairly clear that's the case, but your alternative hypothesis must be based on prior expectation, independent of the data. You have to choose it without even knowing what your data is, basically. So basically, if you have any doubt at all, just use a difference as your alternative hypothesis, and it is the default in all the tests interpreted in R. So basically, your alternative hypothesis will pretty much always be that there is some difference. You don't know which direction or how big, but that's what you're testing for. So once you have your hypotheses, you can collect the data. You can perform your experiment, you can look at the existing data or whatever. The data is the statistical sample, and it's hopefully representative. It's hopefully a random sample of this bigger population. As I mentioned earlier, in the geosciences, you often aren't able to run a controlled experiment. You're looking at things that happened a long time ago in many cases. So it's really important to consider whether your sample is really representative of the population. Are there any biases that could affect your sample? This will be very unique to whatever sort of data you're working with, and if you're collecting the data, then you will hopefully have a good idea of whether what you've collected is biased in some way or not. But that's the key thing, and we're not really going to deal with that. It'll be implicit in all of the future things we'll talk about in this class, that the sample is a good representation of the population. So now we've set up our test. The next video will cover what you do when you get your results. You can put it into R and get the data back and get the statistical test results back. But then the question is, what do they mean? How do you interpret the results of a statistical test? And so that's what we're going to talk about in the next video. The previous video discussed the procedure for choosing a statistical test, given the data that you have and the number of samples, the number of variables. It also discussed how to frame a null hypothesis to be tested. So now we'll cover the interpretation of the results, in particular something called the p-value. So the p-value is, I would say, a highly non-intuitive thing, and it's widely misused, so I'm going to do my best to be precise in this video as I describe things. We'll pick up from the point where you've chosen your null hypothesis and you've collected the data to test that hypothesis. So imagine the case where we want to know if there's a difference in grain size between two samples of sand, for example, the example I've used in the previous videos as well. Well, we collect two samples of sand grains and measure them, and then calculate to the average size, the mean size, and compare the two. So remember that we're using the sample to estimate the population. Even if your samples are unbiased, I mean they're not deliberately higher or lower than the population, you'd still expect two samples to differ from each other to some degree just because they're randomly drawn from the population. So the main point of statistical hypothesis testing is to determine how likely your observations are if the null hypothesis is true. So basically, how likely are your observations if in fact your two samples were independently drawn at random from the same population. Technically, we're going to find the probability of observing an outcome at least as extreme as your result if the null hypothesis is true. So we don't care about your specific result, we care about something at least as extreme or unusual as your result. So one of the outputs from a statistical test is called the p-value. And the p-value is what I mentioned on the previous slide. Now we're just defining it. It's basically the probability of obtaining a result at least as extreme as the observed result if the null hypothesis is true. So the p-value is an important part of the decision process in this type of statistical hypothesis testing. For example, if the two samples did in fact come from the same population, that's our null hypothesis. So if our null hypothesis is true, the two samples did actually come from the same population. So given that, what is the probability of observing a difference in means at least as big as the one we did observe? So note that the p-value is not the probability that the null hypothesis is true. So that's an extremely important point. It's the probability of observing your result if the null hypothesis is true. So it's basically the probability of observing data. It's not the probability of the hypothesis being true. However, even though the p-value is not the probability that the null hypothesis is true, it does tell you something indirectly, qualitatively, about how likely that null hypothesis might be. If the probability of observing the data is extremely small, then it suggests that the null hypothesis is perhaps not that likely to be true. But remember, the p-value is not the probability that the null hypothesis is true. It's also not the probability that the result occurred by chance. So the p-value is just a probability. On its own, it doesn't allow you to make any decisions. You need to pair the p-value with some predetermined significance level called alpha. So alpha is the threshold, and if the p-value is lower than or equal to that threshold, we can conclude that the null hypothesis is unlikely enough that we can reject it. So remember that the p-value again is the probability of observing an outcome at least as extreme as your result in the case where the null hypothesis was in fact true. But what level should we choose for alpha? And what are the implications of that choice? Well, consider this matrix here. It has two rows. The two rows labeled in blue on the left indicate the two possible states of reality. Although we don't know which is the case, and we can't know which is the case, the null hypothesis in reality is either true or it's not true. Again, we don't know which of those it is. The two columns labeled in black at the top, are the two possible decisions that we can make given the p-value from our test. We can either decide to reject the null hypothesis, We would do that if the p-value is smaller than or equal to alpha. Or we can decide that we're unable to reject the null hypothesis. So note that I didn't say accept it, so we can never actually accept or prove the null hypothesis. We just fail to reject it at a particular significance level. So two of the possibilities end up correctly reflecting reality. So if we make those choices under those circumstances, we are correct. But the other two are erroneous conclusions. So if we set the alpha to be really high, let's say I'm going to reject the p-value if alpha is less than 0.5, if there's less than a 50% chance of observing the data that we got if the null hypothesis is true. So if we set alpha to be large, we can reject the null hypothesis for lots of different p-values. If the p-value is 0.4, we can reject it. If the p-value is 0.3 or whatever. So in doing so, we would be more likely to reject the null hypothesis when it was in fact true. And that's called a type 1 error here. So we might be correct, but if we set our alpha to be really high, the chance that we're going to commit this type 1 error is bigger. In contrast, we could be extremely strict and we say, okay, I'm only going to reject the null hypothesis when the probability of observing the results is extremely small. We'll say, I'm going to say the alpha is 0.0001. In that case, it would be really hard to reject the null hypothesis, in which we might be committing a type 2 error. So type 2 error basically means that we did not correctly reject the null hypothesis. So in that case, we're going to reduce our chance of discovering truly significant results, really. So there's a lot of interesting history behind this, but to make a long story short, the completely arbitrary yet conventional choice for the significance level is alpha. Alpha is 0.05. So this alpha again corresponds to the type 1 error rate, but I want to emphasize an important point. So if we set the significance level alpha, the type 1 error rate, to 0.05, that does not mean that 5% of our tests will be false positives, and it definitely doesn't mean that 5% of our significant results will be false positives. So actually, and this is a little complicated, but I will link to a website that explains it in more detail. The proportion of significant findings that you say are significant because p is less than alpha, the proportion of those that are actually false discoveries is a function not only of the significance level alpha, but also of the power that your test has to find results, and of the probability that the effect you're looking for is even real in the first place. So keeping that all in mind, the final step is to compare your results, particularly the p-value, to your chosen significance level alpha, which is 0.05 by tradition. So this means that you would reject the null hypothesis if the probability of observing results at least as extreme as your own findings is 0.05 or 5% or less. So if you reject the null hypothesis, we will say that the difference between samples, or whatever you're testing for, is statistically significant. Note that we can never prove or accept the null hypothesis. If we fail to reject the null hypothesis, it's not correct to say that the samples are the same. You should only say there's no significant difference. So your comparison is either significantly different or not significantly different. You can never say that they're the same. Two final important notes. First, this process that we've outlined in this video and before for statistical hypothesis testing is valid for testing a single hypothesis that you proposed before you looked at your data. So you should never try multiple paths to get to a result. You should never try different permutations of data. You should never try excluding and including things. You should never run multiple tests unless you're reporting that you're doing that. So more on that in future videos. Basically, if you run multiple tests, if you sort of dredge through your data trying to find things, there's the overall chance that you're going to find something that is a type 1 error, that you're going to find one of these false positives or false discoveries is increased potentially a lot. And finally, it's important to note that statistical significance just tells you the probability that the effect exists, the probability of observing an effect at least as large as you did if the null hypothesis is true. It says nothing about the importance of the effect itself. So you need to look at the size of the actual effect, the size of the difference between samples, or the strength of the relationship or whatever, and use your own judgment to determine whether that would be important in the real world. Statistical significance is a function both of the size of the effect, but also the sample size that you're working with. So tiny differences between groups can end up being statistically significant if you have a large sample size, even though they might not be meaningful in a real-world sense. This video introduces the t-test. First, we'll discuss it conceptually and then briefly cover its implementation in R. So the goal of a t-test is to compare the mean between two samples. So remember that statistical methods test a null hypothesis, which must be a unique, testable statement, only one possible outcome. So when comparing means, the null hypothesis is typically that the two samples come from populations with the same mean, or that the population mean 1, mu1 equals the population mean 2. So these are the requirements for performing a t-test, or the assumptions of the test. Your data must be measured with a continuous variable divided into predetermined categories, or groups. You must have univariate data, which means comparing only a single variable between the samples. The t-test compares only two samples, and it's designed to compare central tendency, the mean specifically. And finally, the t-test is a parametric test, so the data must be normally distributed. So if you follow the flow chart, you can see how you go from continuous data, one variable, two samples, central tendency with normal distribution. So conceptually, what are some of the factors that would make you think that two samples come from different populations rather than being two random draws from the same population? Well, if you had these two distributions illustrated here, intuitively you'd probably think that they came from different populations, given that they don't really overlap very much. However, in this example, you'd probably guess that the two distributions came from the same population, given that they overlap quite a lot. These two curves have the same standard deviation as in the example to the left, but the difference is that the sample means is much, much smaller. In this third example here, the difference between sample means is the same as in the graph directly above it, but each distribution has a larger standard deviation, and as a result, you probably wouldn't think intuitively that the two came from different populations. They overlap quite a lot, so they're probably not actually really that different. So intuitively, you can see how, one, the difference between sample means, and two, the standard deviations of each sample are important for determining whether it's likely that the two samples came from the same population or not. In addition, the sample sizes are also important because we actually really care about the standard error, not the standard deviation. The standard error is a measure of the accuracy of the sample mean, how accurately it represents the population mean. So given that, it's probably not surprising that the t-test basically compares signal to noise. The signal is the difference between sample means. The greater the difference, the more likely it is that they came from different populations. And the noise is something called the pooled standard error. It's called pooled because it's a single value that incorporates the standard error of both samples. Basically, although the equations are not important for our purposes because we'll use the computer to do the math, but basically you calculate the common standard deviation simply by weighting each sample's variance by its sample size, or technically n minus 1. And so remember that standard error is just standard deviation divided by the square root of sample size, but this time you divide the common standard deviation in the left by the square root of the two sample sizes together. Okay, so this formula here, this signal to noise ratio, the difference in means divided by the pooled standard error, is called the t-statistic. But to assess its statistical significance in this null hypothesis framework, we need to calculate the p-value, which is the probability of observing a t-statistic at least as extreme as what we got, if the null hypothesis is true, and we need to compare that to our significance level alpha, which is traditionally 0.05. So if the resulting p-value is 0.05 or smaller, we can reject the null hypothesis and say that the two samples do have significantly different means. But to calculate the p-value, we need to know the probability of observing different particular values of t if the null hypothesis is true. So if the null hypothesis is true, the two populations truly have the same mean. So the most probable value for the t-statistic, which is the difference in means divided by the standard error, should be 0. If the two sample means are the same, then you have 0 divided by something and you get 0. However, remember that the two samples are each randomly drawn from their population. And so they may differ just by chance, just because you randomly draw something a little bit bigger or a little bit smaller. So as a result, the t-statistic can be a bit bigger or a bit smaller than 0, even if the null hypothesis is true. So we need to know how big or how small can it be before it is sort of too unlikely. And that's what the t-distribution shows us. It shows us the probability of observing particular t-statistics, which is going to vary with sample size, or technically with what's called degrees of freedom. So when the sample size is small, which is the dark blue line in this example here, more extreme t-statistics are slightly more likely. The curve is slightly higher at the two tails. And that's just because if you have small samples, you're going to sort of maybe more easily randomly choose something a little weird. But remember that the p-value is the probability of observing an outcome at least as extreme as what we found if the null hypothesis is true. So the t-distribution tells us what to expect if the null hypothesis is true, and so therefore we need to find the probability of observing an outcome at least as extreme by looking at the area under the curve more extreme than our given t-statistic. So the p-value is the area under the t-distribution that's more extreme than the value you calculated. But how that is obtained depends on your alternative hypothesis. We discussed this in the previous video, but remember that normally your alternative hypothesis will be that there is a difference in means, but no pre-specified direction. It's that the difference in means is not 0. So if our alternative hypothesis of the differences mean is not 0, we don't know which one is necessarily bigger than the other. Maybe sample 1 is bigger, maybe sample 2 is bigger, but we don't really know or care. So in that case, we're running what's called a two-tailed test. And the p-value is calculated as the area under the curve on both tails. Right? So if you calculate your test statistic and get a t of 2, you need to find the area under the curve greater than 2, but also smaller than minus 2. Because we didn't have a pre-specified direction, and so we didn't know that sample 1 must have been bigger than 2, or vice versa. We just need to know they are different. But if you choose an alternative hypothesis that one sample should have a greater mean, or a smaller mean, this is called a one-tailed test. And in which case you just look at the area under the curve in the direction that your t-statistic actually is. So remember, and this is very important, that you must decide on the alternative hypothesis prior to looking at the data. It's not based on data, it's based on some prior expectation. And so in a one-tailed test, the p-value is based on the area under the distribution beyond the t-statistic in just that one direction. So there are a couple important assumptions that underlie the t-test. First, the two samples must be independent of one another. So this is generally not an issue in the earth sciences, but one way you might get repeated samples, or in non-independent samples, if you have repeated measurements of the same things. So basically, that's the most common way that this assumption is violated. If you have repeated measurements on the exact same objects, you measure the temperature of your lake at noon, and then you measure the temperature of your lake at noon on the next day. Those are repeated measurements of the same thing. And second, as already mentioned, the samples must be more or less at least normally distributed. The test is somewhat robust to this as long as they aren't really skewed. So if you have a peak in the middle and it's got relatively symmetrical shape of the histogram, then it's probably fine for a t-test. The third assumption, which you'll often hear, is that the two samples have equal variance. But this only applies to the traditional form of the t-test called the student's t-test, The default in R is something called Welch's t-test and doesn't make that assumption. Welch's t-test is generally better and you should use it anyway, so we don't really need to worry about this assumption. So as you learned, the first assumption of the t-test and many statistical tests is that the two samples are independent of each other. As I also said, that's not that common in the earth sciences to have repeated measurements or non-independent samples. But what if you do? Like, what say if you're comparing whether two different pH meters give comparable results on the same physical samples, for example. In this case, you should use something called a paired t-test. And so because the pairing of measurements, of observations, is important, the paired t-test calculates the difference between each measurement. So the first measurement for observation 1 minus the second measurement for observation 1, and so forth. So in this case, the difference would be minus 0.2 pH units for the first observation, plus 0.3 for the second, and so on. So the t-statistic, instead of being the difference between sample means, is now the mean difference between paired measurements. And then, just like before, it's divided by the standard error. In this case, the standard error is also calculated from those differences and not from the raw data. And we can just divide by the square root of n. There's no need to worry about the pooled standard error because the number of observations is the same in each of our two measurement categories. So after this point, the calculation of the p-value from this t-statistic works in the same way that it did with the standard test. So here's how you should report the results of a t-test when you're writing a results section, for example. You should give the means of both samples. You should give the type of t-test, Welch's t-test normally, one versus two-tailed. Is it a paired t-test? You should give the value of the t-statistic. You should give the degrees of freedom. And you should give the p-value. So for example, you could phrase your results something like this, where river incision rates were greater in sandstone. Give the mean, then in granite river channels, give the mean of that. Say it's a Welch's t-test with this t-statistic and these degrees of freedom and this p-value. And note that if the p-value is really tiny, you can just write and say that it's less than 0.0001 or something like that. You don't have to say p equals 2.3 times 10 to the minus 10, because really once it gets that tiny, it doesn't matter. It's just highly significant. In the previous video, you learned about the t-test, which is used to test for differences in the mean between two samples. But what if you have more than two samples? Like, say, testing for differences in mean sand size on 3 different beaches, or 4 or 5 or 10 or however many. That's where Anova, or analysis of variance, comes into use. But first, why do we even need a different test? Why not just do a bunch of different t-tests? Well, I'll first of all know that the t-test and Anova aren't really that different at all. They're each just specific cases of a more generic method. But anyhow, there are a couple reasons why Anova is preferred to multiple t-tests. So first, trying to run t-tests between all pairs of samples will add up fairly quickly. The number of tests you need will grow very quickly. Although this isn't such a big deal with some programming these days. And second, and more importantly, really, running multiple tests increases the risk of at least one of the tests being a type 1 error. These problems aren't insurmountable, but largely for reasons of convention, you should perform Anova when you have 3 or more samples. Despite the word variance in its name, Anova is designed to test for differences in mean, with the null hypothesis that all samples come from populations with equal means. So Anova requires continuous data in predetermined groups. One variable, so it's a univariate test, and it's designed for comparisons among more than 2 samples. If you run it on 2 samples, you'll just get the same result as you would get with a t-test. The test compares central tendency, specifically the mean, and when the data are normally distributed. So it's called a parametric test because of that assumption and requirement of a normal distribution. So what does the test do? Well, first it calculates something called the between-group mean square, sometimes called the model mean square. This is just the squared difference between each sample mean the little x bar sub I, and the overall mean, x bar. And that difference between each sample mean and the overall mean is weighted by the size of each sample and divided by the degrees of freedom, which in this case is m minus 1, or the number of samples minus 1. So note that this is basically the formula for sample variance, which you've seen before, and which is the source of the name analysis of variance. So this measures the separation among samples with the idea that all samples should be close to each other and therefore close to the overall mean if they did in fact come from the same population. But second, and this is analogous to the t-test, we need to consider the scatter of data within each sample, and this is called the within groups mean square, sometimes called the error mean square, and this is a double sum of squares. In each sample, you calculate the squared distance from each data point to its sample mean. You do that for all samples and add all of those values together. That sum of squares is divided by the degrees of freedom to give you the within group variance. In this case, degrees of freedom is total sample size n, however many observations you have in total, minus the number of samples m, because 1 degree of freedom each time must be used to calculate each sample mean. So the test statistic, f, is calculated as the ratio of the two variances, the between groups mean square and the within groups mean square. Analogous to the t-test, this is basically a signal-to-noise ratio. So if the separation between samples is very large relative to the scatter of data within samples, the F statistic is large, and it's more likely that at least one of those samples didn't come from the same population as the others. Like in previous tests, the p-value is calculated as the probability of observing an F statistic at least as extreme as what we did if the null hypothesis is true. So we need to know that. We need to be able to figure that out. So if the null hypothesis is true, and if all samples come from populations with the same mean, the between groups mean square, and therefore the F ratio, should technically be 0. Of course, because our samples are small, and because they're randomly drawn from the populations, they're going to differ somewhat a little bit just by chance. So the F distribution, shown in the graph here, basically tells us how likely we are to find particular values of F when the null hypothesis is true. So we compare our actual F value to the distribution of F values expected if the null hypothesis is true, and find the area under the curve more extreme than our result, which is the p-value. So Anova has basically the same assumptions as the t-test. First, the samples must be independent of one another. And in pretty much all data you might have, this is going to be the case. Just watch out for repeated measures on the same things. If you measure the same thing once, and then again later on. That's the most common form of non-independence. All samples must be normally distributed, but I will note that the test is actually quite robust to this, particularly if the sample size is not small, unless the samples are really quite skewed. Finally, there's an assumption called homogeneity of variance. It's basically, which just means that the variances of all the samples should be equal. If the sample sizes themselves are approximately equal, this assumption is less important. But when the sample sizes are unequal, and especially when they're small, you should be careful that the sample variances aren't too different. If that is the case, if you have maybe small samples or if you have very large differences in variance, you could try Welch's Anova in the case where the variances do differ greatly. And it's available in R, but I'm not really going to go into it in any more detail. Okay, so we discussed how the p-value is calculated, and the subsequent inference that you would do from that is standard. If it's less than 0.05, you would reject the null hypothesis. But what does that really tell you? The alternative hypothesis most commonly is that at least one of the samples differs significantly from the others. But how many do, and which ones do? Well, if you obtain a significant overall Anova, often called an omnibus F, you can run a post hoc test. Post hoc just means after this. And so the sort of standard post hoc test for the regular Anova is the Tukey HSD. HSD is for honestly significant differences test. It's basically a set of simultaneous pairwise t-tests that corrects for that problem of doing multiple comparisons. So that controls something called the family-wise error rate. And the family-wise error rate is the probability of making at least one type 1 error. So what it does is it's just the difference between sample means. You run it for all possible pairs of samples, divided by the square root of the within group mean square, divided by something called the harmonic mean of sample size. If you refer back to the t-test video or slides, you can see the similarity between this formula and the t-test formula. So the Tukey test will give you p-values for all pairwise comparisons, controlling for multiple comparisons, so you can interpret them at the traditional 0.05 level. I will note that it assumes equal sample sizes among all your samples and equal variances. So if that's not true, you could try running something called the Games-Howell post hoc test, which I won't describe. So when reporting the results of an ANOVA, you should give the means for all samples. If there are 3 or 4, you can do that just in the text, but you may want a table if there are quite a lot of them. You should report the test name. You do ANOVA, or one-way ANOVA technically. You should give the value of the F statistic, the 2 degrees of freedom, and finally the p-value. So here's an example of how you might phrase such a result. And I'll point out that you should always describe the ANOVA results, and then if they are significant, as is the case here in the example, you should separately describe the result of a post hoc Tukey test. If your ANOVA overall is not significant, there's no need to do a Tukey test because you already know there's no significant difference between the means. So in R, the ANOVA function AOV works a bit differently from the t-test or the f-test that you've done before. You can't just list the samples separated by commas because R doesn't know how many samples to expect. You might have 3 or 4 or 5 or 10. And so because it's not specified, right, the t-test always has 2 and the f-test always has 2. You basically have to use this syntax here, which is the name of the numeric column, which contains the continuous values for your data, the tilde symbol, and then the name of the category column that contains the categorical grouping factors, like what rock type it is, what ocean does it come from, what lake, so forth. So in this case, the tilde basically means like as a function of. So we want to know how does the numeric data vary as a function of the category that it belongs to. And in this case, you can also just write the column names. You don't have to write the data frame $ column name because you specify after the comma there that both columns can be found in a particular data frame. That's what the data equals, and then you would put in the name of the data frame variable that you have. I'll just use data frame, but you would have a real variable name for that. So one thing to do is to make sure to assign this result of the ANOVA to a variable in R so you can store it. For 2 reasons. One is that you'll need to run this summary function to see the full details of the results. And in that case, you'll get something that looks like this. It gives the between groups data, degrees of freedom, sum of squares, and the between groups mean square in the first row. It gives the within groups data, the same stuff, degrees of freedom, mean square. Gives the F statistic, and it gives the p-value, which is, as it sort of illustrates, as it says in the heading there, is the probability of finding an F at least as extreme as what we found. So when you report the results, the degrees of freedom, the F statistic, and the p-value are really the important things, remember. So if you get a significant result with your overall ANOVA, you should next run the Tukey test, and that's the second reason why you need to store your ANOVA results as a variable, because the Tukey test operates on those ANOVA results as its input. So you basically just say Tukey HSD, note the capitalization, and then in parentheses just put in the results from the ANOVA. What you'll get is something that looks like this. Well, I've truncated it. There'll be many more rows in this particular example here. It shows the first column is the difference between sample means. The next 2 columns are the 95% confidence interval on that difference between sample means, between each pair listed there. And finally, you get the adjusted p-value for the null hypothesis that the 2 samples come from populations with the same mean. You'll notice the ones here that say 0, or 0 e to the 0 power, that just means that the p-value is really tiny, and so in that case, remember, just you can report less than 0.001. Previous videos in this series have discussed parametric statistical tests, like the t-test or Anova, which require that the data be normally distributed. So you can use graphical methods like a histogram, as you've done before, to assess that assumption. But what if your question that you have specifically involves testing whether data follow a normal distribution or not? Well, the Shapiro-Wilk test is designed for that purpose. First, a quick description of something called QQ, or quantile plots. They're actually related to the Shapiro-Wilk test, as you'll see in a second. So these plots have the actual data on the y-axis, the sample quantiles, with the values ordered from smallest to largest. The x-axis shows the expected, or the theoretical, normal quantiles. So a quantile is just a fraction of points smaller than a given value. So the x-axis is what you would expect for a normal distribution with the same mean and standard deviation as the data. So if the data are normally distributed, the points here should follow along this straight line, especially in the middle of the distribution. The tails where the data is kind of sparse is a little less important. So it turns out that the slope of this line is actually the standard deviation of the normal distribution. So straight lines mean that it's close to a normal distribution. If the line is curvy, the line of points, it does not fall along that straight line, then it's not a normal distribution. So this is another good way of assessing your data to determine whether parametric tests like the t-test or the f-test or Anova are reasonable to do. But the Shapiro-Wilk test is a formal test of the null hypothesis that one sample is drawn from a normally distributed population. So because the normal distribution is a continuous probability distribution, you can only use this test on univariate continuous data. So the test calculates a statistic called W. So the numerator of this equation here, the sum of AI times xi squared, so that sum is basically the slope of the QQ plot, the slope of the observed data versus the expected values from a normal distribution. It's normalized to a constant and whatnot. So basically, yes, this is the slope of the QQ plot squared. And so if the data follows a normal distribution, this value here, the slope of the QQ plot squared, should be an estimate of the population variance, this sigma squared, but only if the distribution is normal. So the denominator is also an estimate of population variance, and it's just the sum of squares. So therefore, if our null hypothesis is true, and the data are actually normal, W should equal 1, because the top and the bottom of this equation are both estimating the same thing. And so W's values less than 1 may indicate a significant difference from normality. But we also have to consider whether that difference is more than we might expect for a small random sample drawn from a population. Right? It should be 1, but we have a random sample, so it just randomly might be less than 1. So the p-value is the probability of finding a W statistic at least as small as observed if the null hypothesis is true. And Shapiro and Wilk, when they came up with the test, actually calculated the p-values empirically by simulating a whole bunch of normal distributions. So a couple cautions. First, the test can run into problems if your data contain many equal values. There are other tests of normality which we won't cover, and you can check out and some of them might perform better in this situation. The test also has little power to reject the null hypothesis when the sample size is small, and it's very likely to reject the null hypothesis it's very likely to reject the null hypothesis even for tiny differences from normality when the sample size is large. But these two are typical problems of significance testing in general, so as always, make sure to assess the real-world importance independent of the statistical significance. Also, make sure to remember that a large p-value greater than 0.05, only means that you are unable to reject the null hypothesis. It doesn't prove that the distribution is normal. In fact, technically with this type of statistical testing, you can never prove that you have a normal distribution, just that it's not significantly different from normal. And I will also note that you shouldn't use the Shapiro-Wilk test to assess normality for a t-test or ANOVA. If you want to know, is my data good enough for a t-test, the Shapiro-Wilk test is far too sensitive for that purpose. Many data sets that fail the Shapiro-Wilk test, that are significantly different from normal, are perfectly fine for a t-test or for ANOVA. So use histograms or use QQ plots instead. The Shapiro-Wilk test function in R, Shapiro.test, is about as simple as R functions get. You just provide it a single numeric vector as the one argument, called x here. The output is also pretty minimal. It just gives you the test name, the W statistic, and the p-value, and you should report both of those values when summarizing your results. Get the W statistic, the p-value, and actually, although I didn't do it here, you should list the test that you did because there are several different tests for normality. So make sure to also mention that you performed a Shapiro-Wilk test. This video introduces the Kolmogorov-Smirnov test, often just called the KS test. It's the first of the non-parametric tests that we'll cover in this course. So non-parametric tests don't require that the data follow a normal distribution. The previous tests, like the t-test, ANOVA, the f-test, are all parametric tests because they have that assumption of normality. So before discussing the KS test, we need to cover something called a cumulative distribution function, or a CDF. Basically, a CDF, shown on the right here, indicates the probability of a variable being less than or equal to a specified value. So in the CDF shown on the right, the horizontal dashed line indicates a probability of 50%, or 0.5. If we read down from where the function meets that line, it shows that 50% of the values in the data set are less than 0. So the corresponding probability density function, shown on the left, corroborates that, in which there is less than, or which half the area is indeed less than 0. So the cumulative distribution function is just essentially an integral of the PDF evaluated from negative infinity to whatever value x. So back to the KS test. Its purpose is generally to test for differences in the shape between two sample distributions. It can also be used to compare one sample to a known statistical distribution, but we're not going to really focus on that as much as the two-sample test. So the test compares the overall shape of the distribution. It doesn't specifically test for differences in central tendency or dispersion, although those are part of what affects the overall shape of the distribution. So the test, in R at least, requires univariate continuous data, and the null hypothesis for the two-sample test is that the two samples were drawn from populations with the same distribution. They should have the same cumulative distribution function. So the test statistic, given the term D, is quite simple. It's really simple, actually. It's just the maximum absolute difference between the two cumulative distribution functions. So at whatever point those two functions are furthest apart, that distance in the probability is the statistic D. So if the null hypothesis is true, and they do in fact come from a population with the same distribution, D should technically be 0. Of course, in reality, the two samples are randomly taken from their population, so even if the population is the same, they should differ somewhat. So we need to know the p-value, the probability of observing a D statistic at least as large as what we found, if the null hypothesis is true. So Kolmogorov, when he came up with the test, calculated that expected distribution of D if the null hypothesis is true. I won't go into the details of how he did it or what it is. But basically, the p-value is obtained by finding the area under the expected distribution for values at least as extreme as the observed D statistic. So the R function for a two-sample KS test is called ks.test, and it requires two numeric vectors separated by a comma as the input. So you sample 1, numeric vector, and sample 2 is a numeric vector. So the output looks like this. It gives you the D statistic and the p-value. You may also get this warning message at the bottom, which comes up if the sample has at least some values that are exactly the same. These are ties, right? If one of the data sets has the value 12 three times, that's a tie. So in this case, R can't compute the exact p-value, so it just estimates the p-value from a distribution that approximates the true null expectation. There's not much you can do about this. I mean, your data is what the data is. So you pretty much just have to ignore the warning. The p-value will pretty much be fine, as long as you only have a few duplicate values. If you have a lot of them, if you have many duplicate values, many ties in your data, you should probably be more cautious and read into this a little bit more. So when reporting the KS test results, make sure to give the name of the test that you did, the test statistic D, and the p-value. This video introduces the Kruskal-Wallis Test, which is the non-parametric equivalent of Anova. So it tests for differences in central tendency among more than two non-normally distributed samples. So as I said, the purpose of the Kruskal-Wallis test is to examine differences in central tendency. It works on rank order data, so it doesn't specifically test for the mean or the median, but the null hypothesis is that all samples are taken from populations with the same location. And so location in this sense just means the center of the distribution. So the test requires that your data be continuous variables in predetermined groups or samples. Because it is a rank order method, you can also use ranked data. This was the case we saw in the Man-Whitney U test in the previous video. The test is a univariate one, so you must be comparing only a single variable among the samples, but it is designed to handle more than two samples. And as mentioned before, it compares central tendency among the samples, and because it is non-parametric, there is no requirement that the data be normally distributed. So what does the test do? Like the Man-Whitney U test and other non-parametric methods, it pools the samples together and converts the values to ranks. And it then just performs an Anova on the ranks. So the signal, essentially, is the difference between each sample's mean rank and the overall mean rank, weighted for sample size. The noise is the spread of ranks within each sample. So remember from the Man-Whitney U test video that ranks are just the order of the data. So the smallest value will be 1, the second smallest will be 2, and so forth. So with these formulas here, if you compare them to Anova for the between groups and within groups mean square, you can see the similarities. And we're just performing Anova here, but instead of the data, we're using the ranks. And so like Anova, the test statistic, which is called H here, is the ratio of those two values. The signal was essentially the between ranks mean square, you could call it, and the within ranks mean square. But to calculate the p-value, we need to know the probability of observing an H statistic at least as extreme as we did if the null hypothesis is true. So we need to know what is the expected distribution of H statistics for a given sample size in the case of H naught being true. So unless you have quite small sample sizes, small being like 5 or less, which is very small, the expected values for the H statistic, if the null hypothesis is true, come from a statistical distribution called the chi-squared distribution. So the degrees of freedom for this distribution are the number of samples minus 1, which I've written as m minus 1. So the p-value is therefore the area under the chi-squared probability density function curve for values at least as extreme as the observed H statistic. So although the Kruskal-Wallis test is non-parametric, it does have some other assumptions. As in virtually all tests, the samples must be independent of one another, and this is mostly the case in pretty much all sorts of data you'd experience as an earth scientist. The distribution should have the same general shape, like not skewed in opposite directions, for example, and they should have equal variances. But in practice, as long as the variances don't differ by too much, say, like the smallest one, or the biggest one isn't more than like 4 times the smallest one or whatever, you should be okay. But let's say you get a significant result from a Kruskal-Wallis test. That means that at least one of the samples comes from a population with a significantly different location. But which one or ones? There's no specific post hoc test. There's no something like the Tukey test for the Anova, but you can perform multiple pairwise Man-Whitney U tests, but making sure that you have to correct the significance level for doing multiple comparisons. Remember that multiple comparisons will increase the chance that at least one of them is a type 1 error. So one recommended method for correcting this is called the home correction. And it's easiest to demonstrate how it works with an example. So let's say we ran 5 tests, and we got these p-values, which are in ascending order from smallest on the left to largest on the right. Instead of comparing them all to 0.05, the traditional significance level alpha, we have an adjusted alpha. So the first one, which we compare to the smallest p-value, is just 0.05 divided by 5, and we have 0.05 divided by 4, 0.05 divided by 3, 0.05 divided by 2, and finally 0.05 divided by 1, which is 0.05. So we compare the first p-value, we do this sequentially, and we compare the first one to the adjusted threshold, and we can say, yes, this is statistically significant because the p-value is less than 0.01. The second one is also statistically significant, and the third one is also statistically significant, but the fourth one is not because the p-value is greater than our adjusted significance level. And so at that point we stop. We don't even look at the fifth one, even if subsequent values might be below the adjusted threshold. So here's what you should report when you are describing the results of a Kruskal-Wallis test. You should list the medians or give them in a table if there's lot. Even though the method doesn't test for differences in median, it is the best measure of central tendency for non-normal data. As always, you should report the test name, the test statistic H in this case, the degrees of freedom, and the p-value. And so make sure to use the correct phrasing about significantly different versus not significantly different. An example of how you might report Kruskal-Wallis result is given at the bottom here. So our syntax for the Kruskal-Wallis test is basically the same as Anova. The function is called Kruskal.test, and you enter the column name that contains your numeric data and your column name that contains the categorical grouping factors as a formula with the little tilde symbol, meaning like as a function of. So we want to know, do the numeric data vary as a function of the category that they're in? And just the column names are required here. You don't need a $sign or anything like that, because you can specify the data frame name with the data equals part of the function call. So the output will give you the H statistic, which is called the Kruskal-Wallis chi-squared here. It gives you the degrees of freedom, and it gives you the p-value. So the pairwise Man-Whitney U-test function is a bit different in its format. You'll need to specify the data frame and the columns using the dollar symbol style, which you've used before, and you separate the numeric data and the categorical grouping factors with a comma, not writing them as a formula with the tilde. So the output will be a matrix of adjusted p-values. So rather than adjusting the significance level like I demonstrated before, the p-value in R here is just adjusted so you can compare each one to the traditional 0.05. So each entry in the matrix, the triangular matrix of numbers here, gives the p-value for the comparison between the sample listed in the row label and the sample listed in the column label. It specifies the p-value adjustment method at the bottom, which in this case is the home method I described before. You can choose different ones, but the home one is often sort of a preferred one, and so you should just stick with that, which is the default version. This video covers Levine's test and the related Brown-Forsythe test, both of which are non-parametric tests used to look at differences in dispersion. The null hypothesis of these tests is that the samples come from populations with the same dispersion. Both tests require a continuous variable in predetermined categories or groups or samples. They're both univariate tests, but can be used for 2 samples or for more than 2 samples. And the purpose is obviously to compare dispersion. They don't assume normality. However, I would recommend Levine's test even for normal data in the case of more than 2 samples. You can use the F-test if you have just 2 samples, but for more than 2, Levine's test is best because the parametric test, called Bartlett's test, is highly sensitive to even slight non-normality, so just use Levine's test instead. So standard deviation or variance aren't particularly meaningful terms for non-normal data. So these tests instead calculate the absolute deviation of each data point from the center of its sample. So Levine's test calculates the difference between each point and the mean, or often something called the trimmed mean, and the Brown-Forsythe test uses the median instead. So it looks at the difference, the absolute difference between every data point in that sample and the median of that sample. So the reasoning behind this procedure is that samples with greater dispersion will have data points that are further away from the center, and so therefore will have larger absolute deviations from the center. So after converting each point from the raw value to the absolute deviation, the method then performs an Anova on those absolute deviations. Basically, if one sample or more than one sample has larger absolute deviations than the other ones do, you're likely to get a significant Anova result. And using our sort of parallel, that is indicative of significantly different dispersion. So when should you use each test? Well, for more than two samples that are actually close to being normally distributed, you should still use Levine's test, even though the data are more or less normal. But if you have two samples or more than two samples with non-normal data, you have this choice. And so it sort of seems to be rule of thumb that Levine's test using deviances from the mean is best if the distribution is actually still symmetrical, but is what's called heavy-tailed. So sort of flatter and has larger tails than a typical bell curve for the normal distribution. But if you have two samples or more than two samples that are non-normal and are skewed, it's best to use the Brown-Forsythe test for deviances from the median. So basically, Levine's test for symmetrical data, Brown-Forsythe test for skewed data. So here's what you should report. If you're performing the Levine's test, you can probably report standard deviations because it's relatively symmetrical. But for skewed distributions in the Brown-Forsythe test, you should report something called the interquartile range. I didn't mention this in the earlier video, I probably should have, but basically it's just the range from the 25th percentile to the 75th percentile of the data. And you've seen this in the box and whisker plots if you're in the class. So it's also important to give the test name and be clear whether you did Levine's test or the Brown-Forsythe test. Because both tests perform an Anova, you should give the F statistic, the 2 degrees of freedom, and the p-value. So here's how you might phrase your results in the case of Levine's test, where you can report the standard deviation. For Brown-Forsythe, you might want to report the interquartile range, remember. So to run Levine's test, you'll need an additional R package called car. If you haven't used packages before, you can probably find information online about how to load them into your R session. For those in the class, we'll cover it when we meet. The Levine test function has the same syntax as AOV for Anova, or the Kruskal test function. And so you write a formula with the numeric data column as a function of the little tilde symbol, the column containing the categorical grouping factors. And you specify the name of the data frame that those two columns come from with the data equals command. So the default is the Brown-Forsythe test, using the median as the center. But if you want to perform Levine's test using the mean, you just have to specify center equals mean after giving the data. And so the output looks like this. It lists the test name. It gives the 2 degrees of freedom, the F statistic, and the p-value here. The next few videos will discuss tests that you would use for categorical data. But first I want to introduce some background, especially explaining why we even need a different set of tests, as well as some information about choosing the appropriate test. So what is meant by categorical data? Well, it's simply data where you have counts of items in discrete categories rather than measurements of some continuous variable. So some geological examples could be counts of mineral types in rock, counts of rock type in a conglomerate, or counts of fossils at a location or in a time period, or even counts of north or south paleomagnetic direction. Another property of categorical data is that the categories are mutually exclusive. Another way of saying this is that they're contingent. So a rock can't be both sandstone and granite, so that means that more counts that you have of sandstone in a sample of 100 rocks means that you must have fewer granites. More north measurements means fewer south. So the abundance of one category is contingent or dependent on the abundance of the other categories. So here's a hypothetical example where we have counts of rock types found in a conglomerate. So why can't we just use a t-test to determine if there's more rhyolite in this conglomerate than in another conglomerate? Well, the first problem is that we only have a single value. We know there's 37 rhyolites, but we don't have a mean or a standard deviation. We don't know how variable the rhyolite count might be. We could presumably visit a whole bunch of locations and count 100 different rocks at each, but that would be extremely impractical. It'd take forever to do that. But even if we did spend the time and collect many different counts, they're still discrete data. They're not continuous data. And so parameters like standard error or the variance only apply to continuous data. So therefore, tests that use variance or use standard error, like the t-test or the f-test or Anova, don't technically apply to this type of discrete data. So there are actually different statistical probability distributions for discrete data, like the binomial distribution shown down here, which you'll learn about in the upcoming videos. So when choosing what kind of categorical test you want to run, the main consideration is the question that you're asking. In one situation, you might have some prior expectations from theory or from some independent information for what the counts might be. So your goal then is to see if the counts in your sample agree with that prior expectation. So for example, in this sort of somewhat contrived question here, are craters equally distributed in the northern and southern hemisphere on the moon? Well, because both hemispheres are the same size, and therefore each makes up half the surface area of the moon. So our simplest expectation might be that 50% of the craters should be in each hemisphere. You know, we could have a more sophisticated expectation we want, but at the simplest we can say, okay, we should have half in the northern hemisphere, half in the southern hemisphere. So we can then count the craters in each hemisphere and compare that value to our expectation. And keep in mind that the expectation doesn't have to be 50%. That's just the example that we have here. So this type of test is called testing for goodness of fit. You'll typically have one sample, like craters on the moon, and you'll have two categories or more than two categories. So we'll talk about goodness of fit tests in the next video. The other situation is where you have counts in more than one sample. Let's say you counted different rock types in 2 different layers of conglomerates, or in 3 different layers, or many different layers. We have no prior expectation. We have no reason to think that there should be 25% granite or 50% granite. There's no theory or other evidence to tell us that. So we probably instead want to know if the abundances of the different rock types are the same, or are they significantly different in the multiple layers. So in that case, we're performing a test for independence. So more on tests for independence in future videos as well. This video covers Fisher's exact test, which is a method for testing for independence, generally in small samples and in small contingency tables. So a quick recap of tests for independence. The previous video discussed goodness of fit tests, but what if you don't have a prior expectation for abundance? For example, you might just want to know if the abundance of different rock types differs between 2 conglomerate beds. You don't know how much to expect, we just want to know, are they the same in these 2 different beds? So another way of saying this is that the abundance of each rock type is independent of the bed in which it's found. So we want to know, is the abundance independent of the sample that it comes from? So hence the name testing for independence. So the data will come in the form of something called a contingency table, which contains counts of items, the rows, in different categories or samples, the columns. So the item counts are contingent, which means that they're mutually exclusive. In the example here, 1 additional quartz in a particular bed means 1 less chert or basalt, because there's only 50 in total. We often talk about R by C, so R row by C column contingency tables. And this example here is a 3 by 4 contingency table. Some other terminology, if you add up the values in each row, they will sum to something called a marginal total, named because they're the margins of the column. there are marginal totals for the columns as well. So the marginal totals can take on three different cases. In case one, neither marginal total is fixed prior to doing your study. You might have that situation, but most often you'll encounter case two, when one of the marginal totals, either the rows or the columns, is fixed prior to collecting the data. So that's the example here. In this hypothetical situation, we chose to count 50 rocks from each bed. So the column marginals are fixed at 50. However, we didn't know how many quartz or chert or basalt rocks we would find, so those totals weren't fixed beforehand. We had no idea of knowing how many we would come up with. In case three, both the row and the column marginal totals are fixed prior to collecting the data. This is hard to do outside of experiments, so it's not really common in observational earth science data. So Fisher's exact test was designed for 2x2 contingency tables. It technically applies only to those contingency tables where both the row and the column marginal totals are fixed prior to collecting the data, and as I said on the previous slide, that's kind of unlikely for most earth science data. But don't worry, it's okay to run this test anyways, as we'll see in a minute. So the test looks for an association between the two sets of counts, with the null hypothesis that the frequencies are independent between the two samples. So basically, put another way, there's no association among the categories, or there's no difference in the abundance between the different samples. So Fisher's exact test is, as the name indicates, an exact test. So the p-value is calculated as the probability of obtaining an association between the categories at least as extreme as observed if the null hypothesis is true. Right, so the null hypothesis is of no association. The null hypothesis also, you could also say it's that the counts are independent of the sample in which they come from. If that's the case, you would expect the counts to be equal in the two samples, right? If the abundance of chert or basalt is independent of the bed in which it occurs, it has to be the same in both of them. So the greater your observed counts deviate from that expectation of equality, the more likely the result is to be significant. And so the probability of observing a particular outcome in this test is calculated from a type of discrete probability distribution called the hypergeometric distribution. So you've seen a discrete distribution when we talked about the binomial test. And like in the exact binomial test, the p-value here is just the sum of the probabilities for all outcomes at least as extreme as your observation in both directions, right? We have to look in both directions on both sides of the distribution because we didn't have a prior alternative hypothesis that the association should be only in one direction or the other. So a little bit about the hypergeometric distribution and why it matters for this test. So it describes the outcome from a process called sampling without replacement. So to illustrate that, imagine you had a jar with M&Ms or some sort of colored candies in it. There's red ones and green ones and blue ones and many different colors. So you pick a candy out one by one and keep track of what colors you find. But you don't put them back in. So you sample them, but you don't replace them in the giant jar. But because you don't put them back in the jar, the probability of finding a particular color changes over time as the pieces are removed. If you pick a bunch of red candies in a row, the probability you'll find another one actually decreases because you're removing them from the population. So that's sampling without replacement. And it's for this reason that Fisher's exact test is only exact if both marginal totals are fixed. If we fix the marginal totals, that means that the total number of each item is set beforehand, and so removing one changes the probability of finding another. However, when the marginal totals aren't fixed, as in our case 2, where only one of the marginal totals is fixed prior to doing the study, so remember, case 2 is sort of the most common one that you would see in observational data. The test is still applicable even in case 1 or case 2. It's conservative in those cases, and statisticians, when they say conservative, they generally mean that it's not more likely to get a type 1 error. So the risk of type 1 error is not elevated, so I mean, this is not great, but it's not really bad either. So essentially, Fisher's exact test is still the best choice when the counts are small, especially when some are 0, in a 2x2 contingency table, regardless of the marginal total assumption. So when reporting the results of Fisher's exact test, you should provide the contingency table itself, the name of the test, and the p-value. And there's a few different ways which you can phrase the result, but you can use significantly different or not significantly different as you would for other tests. You could say that class composition didn't differ significantly, or that it was significantly different, or you could say the counts of the class were different, or the counts of my observations were different. You could also use the association phrase, but that's maybe less intuitive, and so you could always just go with the counts didn't differ significantly or did differ significantly. So the R function is called Fisher.test, and it requires a single contingency table as the input. And you'll typically have to make that table yourself, either using the function matrix or the function table, which you'll learn in class. And the output will look like this, at least for a 2x2 contingency table it will. The p-values are the key thing to focus on, and for now you can ignore the odds ratio statistics. The 95% confidence interval given here is on the odds ratio. But we haven't talked about odds ratios yet. We will in the logistic regression video in a little while. So for now, don't worry about the odds ratio. You can also perform Fisher's exact test on contingency tables that are larger than 2x2, but in that case, the R results won't give the odds ratio details at all. This video introduces the chi-squared test for independence, which is the final categorical test that we'll cover in this course. So to recap, we test for independence when we have no prior expectation of the counts, but we want to know if the abundances differ significantly among different samples. For example, if we want to test if the abundance of rock types differs between different beds of conglomerate. So the previous video discussed Fisher's exact test, which is also a test for independence. And you should use it if you have a 2x2 contingency table, even if the assumption of fixed marginal totals isn't met. As we'll see in a minute, the chi-squared test isn't well suited as well if some of the counts are very small, and so Fisher's exact test may be better in that case. The chi-squared test does, however, work best for larger contingency tables where nearly all or all of the counts are at least 5, like the example here of rock types in 4 conglomerate beds. So as I just mentioned, the chi-squared test for independence requires categorical data in the form of a contingency table, and can accept any contingency table with R rows by C columns, right, where R is 3 or 4 or 5, and C is whatever number. So the purpose is to test for association between the category counts in the different samples, with the null hypothesis that the frequencies, also known as the counts, are independent of one another among the samples. Another way of saying that is that the counts are equal in all samples, or that they are independent of one another among the samples. There's no association. There's also a chi-squared goodness of fit test, which you may hear about, but you can and should use an exact test like the exact binomial test or the exact multinomial test in nearly all cases. So there's really no need to do the chi-squared goodness of fit test unless you have very large counts that don't work for one of the exact tests. So how does the test work? Well, it compares the observed frequencies to the expectation using the ratio of, on the top is the sum of squares of the deviation, so observed minus expected, and then that's divided by the expected value. So the tables at the bottom show the observed counts on the left and the expected counts on the right. So for example, because there are 91 quartz clasts in all 4 samples, the total of quartz is 91, the expected counts, if abundances were independent of sample number, so the same in all the samples, would be 22.75. So those numbers are fed into the formula. Basically, for each cell, for each row and column combination, you do observed minus expected squared divided by expected. And they are all then added up to give you the chi-squared test statistic. But we want to know whether that chi-squared value is statistically significant or not. So when the overall number is large, so that's n, and when all observed counts O are also sufficiently big, the test statistic can be approximated by the continuous chi-squared distribution. Right, so we have discrete data, but the chi-squared distribution is a continuous distribution. So it's an approximation here. The degrees of freedom for that distribution are the number of rows minus 1 multiplied by the number of columns minus 1, R minus 1 times C minus 1. So in this case, sufficiently large, this is sort of the key assumption of the test, is generally taken to mean that you have at least 50 counts in total. So if you add up all the counts, there's at least 50 individual things that you counted, and no or very few of the observations have counts smaller than 5. So remember that the p-value in all these tests is defined as the probability of obtaining a test statistic at least as large as observed if the null hypothesis is true. And so the chi-square distribution with appropriate degrees of freedom tells us the expected values that the statistic will take if the null hypothesis is true. So we compare our observed value to that distribution of expected values, and the area under the curve, at least as extreme as the observed test statistic, is the p-value. So when reporting the results, you should give the contingency table itself, the test name, in this case chi-square test for independence, the value of the chi-squared statistic, the degrees of freedom, and the p-value. You can phrase your results in terms of a significant difference or a lack of a significant difference in the counts or the abundances of the categories among the samples. So in R, the chi-squared test requires just one contingency table as its input. Now for the type of table that you'll have in the geosciences, it should be formatted so that your categories are the rows and the samples in which you've measured those categories are the columns. So the function is called chi-sq.test, and its output looks like this. It gives the test name and the chi-squared value, which is this x squared, the degrees of freedom, df, and the p-value. And so I ran it to make this example on some unsuitable data. There were too many values that were small, and a number of the values were 0 for the observed counts. So I got this warning message. And you should actually pay attention to this warning message if you get it, because it means that the overall sample size is too small, or more likely that the number of small counts is too great. And so you should pay attention to this and perhaps reconsider whether the chi-squared test is the most appropriate choice of data, or whether you can combine some of your samples to give you a suitable number of counts, suitably large counts, or something along those lines. This video will introduce linear regression, or one method in particular for linear regression. So regression encompasses a broad range of techniques, and we'll just focus on ordinary least squares regression in this video, although I'll mention a few of the other techniques without going into a lot of detail, though. So we've already covered correlation, used to test for an association between variables, where those variables might be interdependent, but they don't have any causal relationship between each other. Regression, on the other hand, is primarily used for one of two goals. It's used when you hypothesize some one-way causal effect, when one variable controls changes in the other. And it can also be used when you want to predict how one variable, which is called the dependent variable, is influenced by the other, and the other one being called the independent variable. So linear regression describes the dependence of one variable, traditionally placed on the y-axis, on another, traditionally x-axis. Basically, how do changes in the independent variable x control changes in the dependent variable y? So the variables have these names because the x-axis one is independent. It can take on more or less any value, but the y-axis one in our hypothesis here is controlled by, and therefore dependent upon, at least partially dependent upon, the independent variable. So intuitively, if we want to determine the best relationship between the dependent and the independent variable, the line that relates those two will be drawn in a way that minimizes the distance between the line and all of the points in our data set. So linear regression requires two continuous variables, and as I mentioned earlier, your goal is generally to test for a causal relationship between the independent and the dependent variables, or your goal might be prediction. So I'll discuss the assumptions and the requirements in more detail later on, but the most basic requirement is that the relationship that you're looking at must actually be a linear relationship. So if we're doing linear regression, and if we're fitting a best fit line to a group of points, the y-coordinate of each point can be described by this formula here. Beta 0, the first term, is the intercept, and beta 1 is the slope of the line. So remember that x is our independent variable, so we're treating it as sort of knowns, but we want to predict how x, or determine how x controls the dependent variable y. Of course, not all the points are going to fall exactly along our line. In fact, probably very few of them will be exactly on the line. So there's this term epsilon, which is called the residual, that measures the distance between our best fit regression line and each point. So this method is called ordinary least squares regression because the line is determined by minimizing the sum of squares of those residuals, but only in the y direction. So for that reason, it's also sometimes called y on x least squares regression. Notice how you could also imagine residuals, the distance from the point to the line in the x direction, but we don't care about those at all in this method. There are other methods for regression that use different ways of minimizing these residuals, but we're not going to talk about those. So the slope of the regression line, beta 1, is calculated as the covariance of the two variables divided by the variance of the independent variable x. And all regression lines will pass through the mean of both variables, so y bar and x bar, the mean of the sample mean for y and the sample mean for x. So the intercept beta 0 can be calculated just from the standard equation of how lines work. So one of the main goals of linear regression is prediction. We want to know how is the dependent variable y predicted by the independent variable x, or how much variation in the dependent variable y can be explained just by knowing the variation in the independent variable x. So this prediction goal can be separate from statistical hypothesis testing. In fact, a statistically significant relationship isn't actually that helpful if the predictive power of that relationship is really tiny. So this is typical of all tests. We need to distinguish the real-world importance from the statistical significance, which itself is a function of sample size and things like that. So the primary measure for the prediction is the coefficient of determination, or r squared. It's calculated as the ratio of the sum of squares of the dependent variable that can be explained by the independent. So this explained sum of squares is basically how much of the sum of squares of y can be explained by x, and then that's divided by the total sum of squares of the dependent variable. So it's often described as the proportion of variation in our dependent variable explained by the independent variable. So in the left panel at the bottom, the graph there, around 35% of the variation in the dependent variable can be explained by the independent, so an r squared of 0.35. Whereas in the right panel, only 4% of the variation is explained, so that's not a very strong or useful predictive relationship. So r squared is the square of the correlation coefficient r, but you should be careful to report r for correlations and r squared only for regressions. Don't mix up the two. R goes for correlation, r squared for regression. So it's also possible to perform statistical hypothesis testing with linear regression. And in this framework, we typically care whether there's a significant relationship, so the method tests whether the slope differs significantly from 0. The null hypothesis is that the variable y is independent of the variable x, or in other words, the slope is 0. So this is a little bit different than the r squared, because the r squared doesn't tell you anything about the slope, it just tells you about how strong the relationship is. So I won't go into a lot of detail, but briefly, the test statistic, the r squared, or sort of the coefficient beta 1 is converted into a t-value by dividing the slope by the standard error, and that value follows a t-distribution with n minus 2 degrees of freedom. So that tells us what to expect if the null hypothesis is true, so we can then evaluate the probability of finding a slope at least as extreme as observed if the null hypothesis is true, the null hypothesis being that the slope should be 0. So there are quite a few assumptions or requirements to do hypothesis testing for linear regression. And I'll explain some of these in more detail with examples next, but first I'll just go through them one by one. So first of all, the relationship must be linear, and both of the variables should have approximately equal variances. Second, the points must be independent of each other. What that means, in other words, is that the residuals, right, the distance from the line to each point, should be uncorrelated. And so what this really means is that you cannot use this ordinary least squares regression on time series data, where you have measurement of some parameter through time, because in time series, almost always, the value at time 2 will be somewhat related to or correlated with the value at time 1 as you're going through this time series. So third, the variance of y must be approximately equal for all values of x. So if you move along the x-axis, there should be about the same amount of scatter in y at all points along that x-axis. And finally, the distribution of the y variable, of our dependent variable, should be normal for all values of x. And so this basically means that the residuals, that distance from the point to the line, should be normally distributed around the line, centered on the regression line, so the mean equals 0. And then it should have a constant standard deviation at all points along the line. So there are ways to relax these assumptions, which I will note briefly, but I'm not going to describe anymore. So you can look into weighted least squares regression if you need to relax the assumption that the variance is constant for all x points. And if you have time series data, you can use either first differences, which is also something called differencing your data. So instead of looking at the raw values, you look at the change from one time to the next. Or you could use generalized least squares regression. So here's one quite extreme example that violates some of the assumptions. The most important thing here is that the residuals are correlated, right? If one point tends to be above the line, the neighboring points also tend to be above the line. If one point has to be below, the neighboring points tend to be below. So they're also not normally distributed around the line. For any sort of given window of x, the values are either above or below the line. And this graph shows an example where the variance of the dependent variable y differs for different values along the x-axis. Variance is much greater here at small values of x than it is at large values of x. So in this case, you could use weighted least squares regression instead of ordinary least squares regression. So when reporting the results of a regression analysis, you typically or often want to include a scatter plot that shows the data and the regression line. And it's often helpful to describe the relationship in words, although this isn't strictly necessary as the plot conveys the same information as the words would. But you definitely should give the coefficient of determination r squared, which tells you the strength of the relationship, as well as the p-value if you're doing hypothesis testing, because that tells us how likely this relationship is to not be 0. So the function for linear regression in R is called LM, which stands for linear model. So you can use multiple independent variables. This is something called multiple regression, which we're not going to cover. But in this case, we're just using a single regression case in this course. And so the syntax is similar to Anova, where you use the function that the dependent variable is a function of, or this tilde symbol, the independent variable. And we often can use the data equals whatever data frame syntax, so you can just give the column name for the dependent and the column name for the independent, and then specify the data frame where those should be found. And remember that the dependent variable for the first one will be on the y-axis in your plot, and the independent variable should be on the x-axis in your plot. So the output is quite complex. There's a lot of things in the output that R gives you for linear regression. But it turns out that a lot of these values, a lot of these items here, are more applicable for this multiple regression where you have more than one independent variable, and we're not really going to discuss that. So I'll just kind of run through what it shows you here. It gives you the distribution of the residuals, the minimum, the maximum, the interquartile distance from first to third quartile, and the median. This can be a useful first point for assessing the assumptions that the residuals are kind of normally distributed, but this doesn't technically tell you that. There are better ways to look at that. But in any case, if you look at this, the residuals should be fairly symmetrical, and the median should be fairly close to 0. And if that is, that means it's a good sign, but you probably want to investigate this more. The second part gives the information about the coefficients. So the intercept row can almost always be ignored. The p-value is testing whether the intercept differs significantly from 0, which is really almost never interesting. So we pretty much just focus on the second row here, In this case, it's labeled with the name of the independent variable. I used SiO2 in this from the GeoRock dataset. And so this gives the regression coefficient, which is the estimate column. It gives the standard error of that regression coefficient. It gives that after being converted to a t-value. And then it gives the p-value for the null hypothesis that the coefficient is 0. In the case of our single regression here, this estimate, the coefficient, is the slope of the line. And so it tells us that because I did a regression of K2O as a function of SiO2, it tells us that K2O increases by 0.12 percentage points for every 1 unit or for every 1 percentage point increase in SiO2. If there were more independent variables, they would be listed below here. You just get several rows of your different independent variables. So the final part gives a variety of information on how well this linear model fits the data. It gives you the standard error, residuals. It gives you 2 R-squared values. The adjusted R-squared on the right there is more useful for multiple regression because it makes some adjustments for the number of parameters if you have more than one independent variable. So in the case of our single regression, we can just use the multiple R-squared, which is what you would use if you only have one independent variable. The f-statistic in the bottom line tests the significance of the overall model against a model that just uses a straight line at the intercept. Again, this is more relevant for multiple regression. In the case of single regression here, the p-value for that will be the same as the p-value for the regression coefficient itself. This video covers ANCOVA, or analysis of covariance, which is a method for testing basically whether regression lines differ significantly, either in slope or in intercept, between different categories, between different levels of a factor. For example, in this graph here, does the relationship between K2O and SiO2 differ between rocks from Archean cratons in blue or rocks from not Archean cratons in pink? So I'll point out, just as you may notice, that many of the regression assumptions are violated by this example shown here, but that's kind of not really pertinent right now. So we're not going to really get into the theory of ANCOVA. I'm just going to focus on a sort of general description of what it does and what it requires so that you know whether it's the sort of test you might need, and it may be worthwhile to read more about it if you're going to actually use this seriously. So first, let's take a step back and talk about something called general linear models. You've actually learned about several of these, despite the fact that I haven't used this term before. So consider having a single, continuous, dependent variable. If the independent variables are also continuous, this is called linear regression from the previous video. So this equation is similar to what you've already seen, except here you can have multiple independent variables, x1, x2, and so forth. But if the independent variables are instead categorical factors, we actually have Anova. So Anova is actually an example of a type of general linear model, and it's actually related to linear regression, except the factors, which I've given like x hat and x2 hat here, are treated as something called dummy variables, where they're just coded as 0 or 1 for the different levels of the factor, for the different categories that they belong to. So ANCOVA is a type of general linear model when you have a mixture of continuous and categorical independent variables. You can think of it as like an extension of Anova or an extension of linear regression, but in reality all three are just specific cases of the general linear model. So ANCOVA tests whether the linear model differs for different levels of a categorical factor. So is the relationship between continuous variable x1 and y different for different levels of the grouping factor x2? So we'll come back a little bit to general linear models later in the course when we discuss model comparison, but for now we'll just move on and talk about ANCOVA. So in the simplest case, where we have a single continuous independent variable on the x-axis here, and a single independent factor with two levels, the blue or the pink, this factor could affect the dependent variable, for example, in a simple additive way, like in the upper right. So basically, in the upper right, we have a 1 unit increase in the continuous independent variable causes a 1 unit increase in the dependent variable. That's true for both lines, but in one category that line is just shifted 1 unit up. So that category has an additive effect, so basically it takes that relationship and just adds 1 and shifts it up. It's also possible, like in the bottom row, that the category factor could have some sort of non-additive effect, and this is called an interaction. So in this case, the slope differs, and that means that continuous independent variable can either have a stronger or a weaker effect on the dependent variable, depending on which category we're looking at. So in both cases, the blue category has a steeper slope, therefore the independent variable has a stronger effect on the dependent variable than it does in the other category. So ANCOVA, or analysis of covariance, requires one continuous dependent variable and at least one continuous independent variable, like in linear regression. But it also requires that the data is divided into categories with at least one categorical or factor variable. So its purpose is to test for a difference in the regression relationship, either in the slope or in the intercept, between these categories, between the levels of this factor variable. And the null hypothesis is that there's no effect, so that category membership doesn't matter what group the data belongs to, the regression slope and intercept is the same. So the first step in ANCOVA is to test a general linear model, a GLM we'll call it here, that includes an interaction term between the independent variable and the factor variable. So if that interaction is significant, that indicates that there's a non-additive effect, and that means that the strength of the relationship, or the slope of the line, differs depending on the factor level. So if you find a significant interaction, that tells you that the slopes differ significantly, but actually that's as far as you can go with this. I'll talk about the next step, but it turns out that having an equal slope is an assumption for the next step. However, if the slopes don't differ significantly, you can then test a second model to see how the dependent variable is affected by the category, holding the independent variable constant, and how the dependent variable is affected by the continuous variable, holding the category constant. So this is an example of something called multiple regression, where you basically look at how each independent variable affects the outcome, sort of while controlling for all the other changes in the other variables. So we don't have an interaction here, but so basically if the categorical term in the model is significant, that indicates that they have a significantly different intercept. I'll show an example of this when I show you how to do it in R at the end of the video. So ANCOVA has all the linear regression assumptions. The first 4 are the same assumptions that you would have seen in the linear regression video, but it also has a further requirement that the linear regression slopes have to be equal for all of the groups or all the levels in the factor. So that's if you want to do the whole thing. I mean, you can definitely test for significant differences in the slope as the first part, but you can only test for differences in intercept in the second part if the slopes don't differ significantly. So ANCOVA is sort of like an extended version of Anova. They're all types of general linear models. So you'll end up with an F statistic. And to sort of report your results, you would often want to give a scatter plot with the data, and it helps to have, say, color-coded points or use different symbols for points, and then you can have different regression lines with different colors or symbols for the groups to indicate how their slopes and intercepts may differ. You should also, of course, report the test name and the F statistic, the degrees of freedom, there are 2 of them for an F statistic, remember, and the p-value. And so if you tested 2 models, one for slope, and then if that was okay, then you moved on to the intercept one, you will have an F statistic, degrees of freedom, and a p-value for each of those 2 models. You would want to talk about them one and then the other, or whichever one is sort of relevant to the question that you're asking. So because ANCOVA, Anova, and linear regression are all cases of the general linear model, you can actually perform ANCOVA either with the AOV Anova function or with the LM linear regression function. So I'll illustrate the procedure here with the Anova function AOV. I think it sort of requires one less step, and it's also similar to what you've already learned for Anova. So the first step is to test the model that includes this interaction term. And so in R, that's denoted with the multiplication symbol. So we have the dependent variable column as a function of this tilde symbol that you've seen before for linear regression and for Anova. Then you have the independent variable column multiplied by the factor variable column, indicating that they all come from a particular data frame with whatever name that has. So the output will look just like the Anova output did, but with extra lines. So we first focus on the interaction term, which is the one containing the colon, so in this case delta CO3 colon species. In this example, the F statistic for the interaction is 5.009. There are 2 and 36 degrees of freedom, and the p-value is 0.012. We can ignore the other two lines for now, although they tell you how the continuous variable and the factor variable affect the outcome, independent of each other and independent of the interaction. So in any case, the interaction indicates a significant difference in slope among the three types of categories of species here. So technically we have to stop here. But I'll proceed and demonstrate how to test for intercept even though we haven't actually met those assumptions. So remember, if the interaction is not significant, which wasn't the case here, it was significant, but if it's not, you can then test whether the factor is significant, where that would indicate a significant difference in the intercepts of the lines. So that's done by including both the continuous independent variable and the factor variable as additive terms in the function, so use the plus sign, not the multiplication sign like from the last slide. And so the output will look the same, just we won't have the interaction line here because we didn't test for it. And so in this case, we want to read the data from the line for the factor variable, which is species. And so the format for the F statistic and the degrees of freedom and the p-value are the same. And those three pieces of information are the key things that you should use when you're summarizing your results in writing. This video covers the last regression technique we're going to discuss in this class, and that's logistic regression. So we've covered linear regression beforehand, where you want to test if two continuous variables are related to each other. But what if the dependent variable has a binary outcome? So binary or binomial means that there's only two outcomes, yes or no. So for example, does size affect survival of organisms during an extinction event? So this is binary because there are only two possible outcomes. They either go extinct or they don't go extinct. So why can't we just fit a linear regression line like I've done here? Well, let's think back to the assumptions that linear regression makes. So first of all, the relationship of the actual data is not linear. I mean, I put a linear line through it, but that's not the relationship that you see from the points. More importantly, the variance of the y values is not constant for all x. It's going to be sort of greater variance in the middle where you have a lot of data at both 0 and 1, but as you get close to large sizes, the variance is quite small because there's very little data at the 0 line. And also, the residuals in the y direction around this red line are certainly not normally distributed either. They're bimodal, in fact. Conceptually, a linear regression fit could also imply that we would get probabilities greater than 100% or less than 0%, and that doesn't make a lot of sense. So that's where logistic regression comes in. It's designed when you have at least one continuous independent variable and a categorical dependent variable. And so the dependent variable must have only two levels in that category. So it's binomial or binary. Like other regression methods, the purpose of logistic regression is to test whether the independent variable, the continuous one, has a causal effect on the outcome of the dependent variable. And the null hypothesis is that there's no effect, so that changes in the independent variable do not change the probability of the outcome happening. Size does not affect the probability of extinction. So a couple of slides ago I mentioned that one of the problems with applying linear regression, aside from the fact that this sort of data violates almost all the assumptions, is that it can imply probabilities greater than 100% or less than 0%, which obviously can't be correct. So we need to find a way to make sure that the probability is always between 0 and 1. And so one way is to use a function to transform the numbers from the range between minus infinity and positive infinity to the new range of between 0 and 1. So a function is just an equation that maps numbers from one range, called a domain, to a different domain. So we're going to map numbers from the domain between minus infinity and positive infinity to the new domain between 0 and 1. And logistic regression uses a function called the logit function, which is this equation given here. So here's how the method works. Remember, the linear regression equation describes the dependent variable y in terms of an intercept, beta 0, a slope, beta 1 times the x value, and then each point is going to have some residual because not all points fall exactly on the line. So if we do that, we get something like the red line in the top graph here, which is obviously not a good description of the relationship. But after applying this logit function, we then get the equation at the bottom where pi I is the probability now that the outcome occurs. So pi I is the probability that y equals 1. And so the regression line now, after transforming it with the logit function to get 1 over 1 minus e to the minus equation there, gives us is now bound between 0 and 1, which is what we want, this curved regression line here. So this equation here is the equation for logistic regression with the pi I, but it's more common or more typical to see the equation in this rearranged form, expressed as the log of pi sub I divided by 1 minus pi sub I. And so that is called the log odds. This log of pi I over 1 minus pi I is the log odds. We'll discuss odds in a bit more detail in the next slide, but briefly, the odds are the probability of an event occurring, pi I, divided by the probability of the event not occurring, which is 1 minus pi I. And so these are log odds because we're taking the logarithm of that odds. So in our equation here, and we have at the top, a positive coefficient beta 1 means that the odds of the outcome increase. And so the probability pi I also increases. So as the independent variable x increases, the odds of the outcome also increase. So I'll just very briefly mention how the significance testing works, but it's not that important particularly. It's analogous to linear regression. So linear regression assesses the significance of our test statistic against the t-distribution, where logistic regression uses a normal distribution. So we evaluate the probability of finding a coefficient which is converted to this z-value. So we want to know what's the probability of getting the coefficient at least as extreme if the null hypothesis is true. So this is fairly standard p-value calculation. Okay, well, back to our coefficient. So this logistic regression coefficient beta 1 is something called the log odds ratio. So this is different than the log odds because an odds ratio is comparing the odds between two different groups. So for example, we can say in case 1, the odds are the probability of success divided by 1 minus the probability of success. That's the definition of odds. And we can have the same in case 2, same way that odds are calculated. And so the odds ratio is just the ratio of the odds for case 1 divided by the odds for case 2. And so in This video discusses the Hotelling t-squared test, which is basically the multivariate version of the t-test. So remember that multivariate data means you have measurements of more than one parameter from each sample. For example, you want to compare pH and oxygen and chlorophyll, those are the three variables, all together from two different lakes, and those two lakes are the two samples. So that's what the Hotelling t-squared test is for. It's designed to test for a significant difference in the multivariate mean between just two samples. And so because it compares just two samples, it's the multivariate counterpart to the univariate t-test. The null hypothesis is that the two samples come from populations that have the same multivariate mean. So the multivariate mean you can think of as a point in space defined by the means of all the individual variables. So it's not like it's comparing each variable separately, it's comparing the point in space that's defined by the mean of all the variables together. So what does the test do? Well, the test statistic t-squared is based on the Mahalanobis distance between the two sample means. The covariance matrix here, so if you need a refresher on the Mahalanobis distance, the previous video discusses that. The covariance matrix here is something called the pooled covariance matrix, which is just the covariance matrix for each sample weighted by the sample size, or technically by the degrees of freedom. So if you think back to the t-test, you can see how this is quite similar to the pooled standard error in the t-test. So if the null hypothesis is true, and the two samples do in fact come from the same population, there should be no difference between their multivariate means, and the t-squared should therefore be 0. Of course, our samples are randomly taken from their population, so t-squared will be greater than 0 just by random chance. But as with all tests, we want to know how big can the t-squared value be before we will reject the null hypothesis that they do come from the same population. So the significance of the t-squared is assessed by converting it to an F statistic using this formula here. So in the formula, n is the total sample size, the total number of observations from all samples, and k is the number of variables. And so then we test this F value against the F distribution with k and n minus k minus 1 degrees of freedom. You've seen F distributions before with Anova, with the F test itself, with a variety of tests. It's a common statistical distribution that we use to determine sort of what is the expected values under the null hypothesis. So the p-value, as typical of all tests, is the probability of obtaining a t-squared value after it's been converted to an F statistic at least as extreme as observed if the null hypothesis is true. And so the F distribution with the appropriate degrees of freedom tells us the expected probabilities of finding particular values in the case where the null hypothesis is true. So this distribution here shows us what to expect when the null hypothesis is true. So if we want to know the probability of finding a value at least as extreme, we just need to look at the area under the distribution at or beyond the F statistic that we obtained in the test. So the Hotelling t-squared test is a parametric test, and so it has many of the typical parametric assumptions. Of course, the two samples must be independent of one another. This generally means you can't have repeated measures of the same item, so you're not measuring the same thing at multiple times. Both samples must be multivariate normal, which means that all the variables should themselves be normally distributed. If the sample size is large enough, this isn't such a big deal. Both samples should have equal variance-covariance matrices, and I'll illustrate that on the next slide. So if you do get a significant result, that means that at least one variable or some combination of the variables differs significantly. It really means that their multivariate mean differs significantly. So it's actually possible that no single variable has a significant difference, but there could be some significant effect when you're looking at them all together. So normally you're running this multivariate test for a reason, because the variables are related and you do want to know how they differ together. But if desired, you can do t-tests on the individual variables after the fact. Make sure to correct for type 1 error risk that you would get by doing multiple tests. You don't see this that often. I mean, generally you're running the Hotelling t-squared for a reason, because the variables are related and you want to know generally how they compare together. So this slide illustrates some of the issues with variance or with covariance of the matrix of the samples. So remember, one of the assumptions is that they have to have equal variance covariance matrices, and you can't really look at the matrix. I mean, you can look at the matrix, but you can't really tell what's going on with it. So you should just look at this graphically. So in the left panel, the two samples have different variances, at least in the variable on the y-axis. The x-axis variable, they have sort of similar variance. This probably isn't too serious of a problem because the covariance of those two variables is quite similar. The right graph is a more serious problem because the covariance between the variables differs quite greatly between the two samples. The red sample has positive covariance and the blue one has negative covariance. And this is a worst case scenario. Obviously, it's pretty unlikely for the same two variables to have opposite covariance, but it is useful to plot variables against each other in your samples to examine both their variance and their covariance and make sure that they're more or less similar. So the Hotelling t-squared test is fairly robust to these deviations from these assumptions, particularly if it's not normal, as long as the sample size is fairly large. You could run, for example, Levine's test to see if the variances are equal. And there's also this test called Boxes M to look at the covariance matrices, but it's generally not recommended. I mean, both of these tests are too sensitive, particularly if your goal is only to assess the assumptions. The Boxes M test apparently is very sensitive to non-normality, so it will often reject the null hypothesis that they have equal covariance matrices, even if it's totally fine for a Hotelling t-squared test. So as with the t-test and previous tests, the best approach for assessing the assumptions is to look at them graphically, rather than running specific tests. You should only run specific tests if that is your hypothesis, if that's the scientific question you have, not to assess assumptions. So there's a lot of information to report for the Hotelling t-squared test. You should give the means of all the variables in the two samples. If there's a lot, a table might be appropriate. Some kind of graphical presentation, like box and whisker plots, could also be useful. Obviously, you should tell what test you ran. Give the t-squared statistic, the f statistic that it gets converted to, and its 2 degrees of freedom, as well as the p-value. So in R, there's no Hotelling t-squared test in the basic version of R, although there is Hotelling t-squared test in different packages. But what you'll do in class is actually write your own test to do Hotelling t-squared. So that's why I'm not going to explain how to do it in R, because you will do it yourself. This video introduces the last of the classical frequentist methods for null hypothesis statistical testing that we're going to cover in this class. It's called multivariate analysis of variance, or MANOVA, and as its name suggests, it's the multivariate version of ANOVA, which you've already learned about. There are a lot of conceptual similarities between MANOVA and the univariate ANOVA, so let's quickly recap what ANOVA does. So remember that ANOVA assesses the differences between the groups by comparing the between groups mean square, right? It's a difference, it's basically the sample mean relative to the overall grand mean of all samples. And it compares that to the within groups mean square, which is the scatter of data within each group. So basically each observation subtracted from the sample mean, sum of squares, and so forth. And so the test statistic is the ratio of those two values. So the purpose of MANOVA is to test for significant differences in the multivariate mean, so you have more than one variable per sample, among more than two normally distributed samples. The null hypothesis is that the samples come from populations with identical multivariate means. You could also phrase this as saying there's no difference in the multivariate means between the samples, or between the populations that they come from. So what does the MANOVA test do? Well, like ANOVA, it compares the differences between each sample mean and the overall mean relative to the scatter of data within each sample. And I won't get into the math, but the difference in means, which is sort of our signal in this ratio, is something called the between groups sum of squares and cross products matrix. So in Anova, it was just the between group sum of squares, but given the fact we have multivariate data here, we have to consider both the sum of squares within each variable as well as the cross products between of the variables. The scatter of data within the samples is called the within group sum of squares and cross products matrix. Like in Anova, the test statistic is the ratio of the between groups to the within groups matrices, which gives us this test statistic A. Remember, in Anova, it was just the between groups divided by the within groups as well. On the left for Manova, it's written in terms of matrix multiplication, and it's just, they're not matrices, they're just numbers in the Anova. So like in all tests, we need to evaluate the probability of finding an A statistic, and A is actually a matrix in this case. We need to evaluate how extreme A is relative to our expectation if the null hypothesis was true. And it turns out that there's no single, unique, correct way to evaluate that extremeness. This is because of the multivariate nature of the data. And so as a result, there's at least 4 different statistics that have been devised, each using the eigenvalues of the matrix. So this lambda term are the eigenvalues of the matrix A, the result of the test. So this Wilks's lambda, the second one, is apparently a commonly used one. It's also Hotelling-Lawley trace. The Pairwise trace is the default version in R. I guess it's often also said to be fairly robust, but there is debate over this. In any case, for our purposes, you can just use the Pairwise trace for the class. It's the default in R, and that's simple enough. So all of these values, the Pairwise trace or Wilks's lambda or whatever, are converted to an approximate F value because of this sort of multivariate nature, and then tested for significance against the F distribution. So the assumptions of Manova are typical, again, of parametric multivariate tests. All the samples must be independent of one another, as well as being multivariate normal. So like many parametric tests, particularly for central tendency, Manova is fairly robust to non-normality, as long as the sample sizes are large, and as long as the variables aren't really skewed. The samples must also have equal variance-covariance matrices. You often see this referred to by a technical term, homogeneity of variance-covariance matrices. So there's a lot of things to assess, especially if you have lots of samples and lots of variables. But the best approach is to assess them graphically. Hypothesis testing for these assumptions, you can test for multivariate normality, you can test for equality of variance, you can test for the variance-covariance matrix equality with proper tests, but they're too strict for evaluating the assumptions. And yes, this will take a while to assess all these assumptions because you need to look at each variable within each sample as well as the covariances, so you'll be making a lot of graphs, a lot of histograms. You know, it gets quite complicated when you have this data, which is itself a fairly complicated setup. So when reporting the results, you should give the means of all the variables in all the samples, and this will likely be a table because it's fairly complicated. If you only have 2 variables, you could make a scatter plot with the samples color-coded or using different symbols, perhaps. But if you have more than 2, it's very difficult to graphically show these. You should give the test name, of course, report that you did Manova, the value of the statistic. Make sure you list whether you use Pairwise trace or Wilks's lambda or whatever. Give the approximate F value and its 2 degrees of freedom, and the p-value for the test. So like at the bottom, it would be an example of how you might report these test statistics. So the Manova function in R is deceptively simple. But remember, there's a lot of assumptions and a lot of complexities with sample design. You know, things like unequal sample sizes, things like covariances between the variables can both be issues. We're just going to gloss over all of that because I'm not focusing specifically on the data that you might have. But if you're using this for sort of real work, you probably want to be careful and really assess whether what you have set up in terms of your sampling is good for Manova. So the Manova function, called Manova, has the same syntax as the Anova function AOV, which you've already used, or linear models. You use this formula input with the numeric data as a function of the category column in a particular data frame generally. The difference here is that the numeric data must be a matrix because we have multivariate data. You'll have multiple columns in a matrix for each of your variables, as opposed to Anova, where you just have a single vector for your data. So you should store the Anova result as a variable and then run the summary function to see the details. The output is quite brief. This is basically all you get for the output, but it gives you all the details that you need. I'll point out that there are two sets of degrees of freedom. There's, on the left, there's the df column, 3 and 978 in this case. But actually the one that you want for your approximate f is the box with the numerator and denominator df's 9 and 2934 in this example here. So those are the ones that go with the approximate f that you're reporting. The summary function is where you can choose the test statistic if you didn't want to use the Pillai trace. That's, you can see that's the default here. But you can select Wilks's, Lambda, or Hotelling-Lawley, or other ones. So just a final word, we haven't covered tests for all the possibilities. If you look at your flowchart, there are a number of outcomes, particularly on the multivariate side, that haven't been filled out yet. And this is partly because a lot of these goals are pretty esoteric and not really that widely used. I mean, there aren't very many situations where you want to test for differences in dispersion for multivariate non-normal data, for example. There are multivariate tests for dispersion, as well as non-parametric equivalents for Hotelling t-squared and MANOVA, but there's often a number of different possibilities because there's no real unique solution for multivariate extremeness. I will mention this thing called per-MANOVA or permutational MANOVA as a possibility if you have non-normal data and want to do MANOVA. It does seem to be fairly widespread, at least in the biological literature. But we're not going to cover tests for all these specific situations because you're not likely to encounter them. They're a bit more sophisticated than we really need for 99% of our data analysis. So you can look into them later on if you need to for your particular work. I also point out that we are going to cover an approach called resampling methods, which includes like randomization and bootstrapping. These will be covered in the next week. And these are sort of the ultimate in non-parametric distribution-free statistics. You can use resampling methods for all these bizarre problems you might have about multivariate tested dispersion. And you can use resampling methods for all sorts of other situations that might be challenging for traditional statistics. And so that's where we're going next, and then we'll move on to sort of more data analysis things in the last few weeks of the class. This video is the first introducing a very powerful group of techniques called resampling methods, which includes something called bootstrapping. So first we'll focus on the case using bootstrapping and these methods to estimate uncertainty, like confidence intervals, on a single parameter. So let's start with a motivating question like this one. What is the 95% confidence interval on this r-squared value? We calculated that r-squared was 0.52, but what's the uncertainty? There isn't a standard calculation for this, but we can use a resampling method to get this information. They turn out to be extremely flexible and powerful techniques, and you can use them for really almost anything that you want to do. So you might remember that the definition of a confidence interval on the mean. So we'll step back from the r-squared and talk about the mean first, because it's a simpler example and we can demonstrate how the method works. So basically, if you took many random samples from the population, 95% of those confidence intervals would include the true population mean mu. So I will illustrate how this works if we had a known population. So the curve on the left is, say, our known population with a mean of 3. So if we can sort of simulate this method by saying, okay, well, let's take a random sample of 100 values from our population with a known mean and a known standard deviation. We'll calculate the mean of that sample. So the green dot is now a sample mean, which is an estimate of our original population mean. We can repeat that process many times, like 10,000 times or whatever, to generate something called a sampling distribution of means. So each of these green circles here now is a sample mean. So for each one, we've drawn 100 values, say, from our population and calculated that sample mean. So if we do that, say, 10,000 times, we get a distribution like this. This is a sampling distribution. It's not the original data. Instead, each point that makes up this histogram is a sample mean that we calculated from one random sample drawn from the population. And so given our definition of a confidence interval, it's just between the 2.5th percentile and the 97.5th percentile, the range that encompasses 95% of the sample means in our repeated trials. So I point out this is just one way of calculating these confidence intervals. It's called the equal tail method. It works best for symmetrical data. If you have a lot of skewed data, there are other methods that we're not going to talk about in this course. So that's fine. Okay, if we actually know the population parameters, but we never know them, right? We never know the population. We just have a sample. We have a single sample, something like this. So what can we do in this case? Well, it turns out that the sample is still the best information we have about the population. I mean, it happens to be the only information as well. And most samples, especially if they're big enough, do indeed closely resemble the population that they come from. So we can make some inference about the true population from this sample here. And essentially what we can do is we can resample this data with replacement. So sampling with replacement means that when we draw a value, we sort of put it back into the pool, we can draw it a second time. So we can resample a single observation more than once. And because some observations might be sampled twice or three times or even more, others may not be sampled at all. So this process of sampling with replacement extrapolates somewhat, at least, to the broader population. So it's a little bit more like our original model of drawing repeated samples from the population. And so this is a process called bootstrapping. This sampling with replacement is called bootstrapping. So we calculate the mean of that bootstrap sample, and we repeat this process many times to generate a bootstrap sampling distribution of the means. So you may be thinking this sounds like cheating. How can we get more out of our data than actually is there? We only have this sample. How can we extrapolate the population? Does this even work? I guess the name bootstrapping kind of acknowledges that bit. It's from the saying, you pull oneself up by the bootstraps, which obviously you can't lift yourself off the ground just by holding on to your shoes. But it turns out that bootstrapping is really an okay thing to do. I'm not going to go into the theoretical justification. You can certainly read more on your own if you're interested. But just trust me that this is a technique that works, and it's not cheating. So the bootstrapped resampling distribution will look something like this. So this is basically taking 10,000 random samples from our single data set, but sampling with replacement. So just to compare, if you calculate the mean and the 95% confidence intervals using our parametric methods that you've used before, you get these values like 2.82 and 3.23 for the confidence interval. And it turns out that the 2.5th percentile and the 97.5th percentile of our bootstrapped resampling distribution gives you the same answer. It's not exactly the same because it's a random sample, but that's kind of beside the point. You can see that it's effectively the same thing. So this sort of demonstrates how the method works with something that we know, like the confidence interval on a mean. And you can use this same approach to calculate confidence intervals on things like the R-squared value that lack one of these standard formulas. So bootstrapping is resampling with replacement. So it maintains the data structure. We have the same number of observations or whatever, but it reshuffles the values to sort of extrapolate to the population. So as I mentioned before, each value can be sampled multiple times or not at all. The example on the previous slide is sort of trivial because we already had a formula for the confidence interval on a mean, and so we could just use that. But bootstrapping is useful in many other situations, like for non-normal data, when the mean and that confidence interval formula don't really apply. The really big benefit of bootstrapping is to estimate statistical parameters for things that have unknown properties, say like the results of principal components analysis, or PCA, which we'll discuss in a few weeks. Or we can use it to bootstrap estimates on things that don't even have a standard calculation, like R-squared in our example, or the coefficient of variation. So there is one caution, and that is to note that some parameters are inherently biased during this bootstrapping process. So measures of dispersion, like standard deviation or variance, are really the most common example of these biased parameters. So let's say that I resample this data on the left here with replacement, as our procedure for bootstrapping calls for. Remember that we can sample values multiple times or not at all if we're sampling with replacement. But the extreme values, the ones, say, near the edge of our data set, tend to be rare compared to values in the center, at least unless your data are bimodal, but for typical data which are relatively symmetrical and have a peak near the middle, the extreme values on the edges tend to be rare. And so that means that when we're doing our sampling with replacement, we're maybe more likely not to collect them than we would be to sample the ones in the center. So that means that we tend to underestimate the range of variability in the data, and the bootstrapped standard deviations are sort of systematically underestimated. And that's what you see on the right there. These are the sampling distributions of just regular bootstrap standard deviations, and that distribution, the histogram, if shifted a little bit to the left of the expected, or the value from our original data. And so because it's shifted a little bit to the left, the confidence interval will be shifted and offset a little bit as well. There are a variety of ways to correct for this, but we'll just cover sort of one fairly straightforward and simple one, and that's called the balanced bootstrap. And so the process just involves correcting the offset by adjusting each value. So each bootstrapped, say, standard deviation in this case, so for each one, we're going to add the difference between the observed value in our original data and the mean of all of our bootstrap data. So we're sort of adjusting each value and shifting it so that the mean of our bootstrap data is the same as the actual value in the original data, the observed value. So in the previous example, the mean bootstrap value is about 0.08 units smaller than the observed value from the original data. So we just add 0.08 to each of our individual bootstrap trials. We do 10,000 of them, so we add 0.08 to each of those 10,000. And that shifts the sampling distribution a little bit to the right. So now it's centered on the observed value, which you see in the balanced bootstrap on the right there. So far in this course, we've been discussing statistical tests to assess specific null hypotheses using distributions and p-values and so forth. But this video introduces the new type of technique called ordination, and specifically we're going to talk about principal component analysis in this video. These ordination methods are types of data analysis that are designed primarily to simplify and to visualize sort of complicated multivariate data in order to aid in the interpretation of underlying processes that contribute to that data. So a lot of the data that you encounter as a scientist or a geoscientist is multivariate. There are counts or measurements of many different variables in many different sites or samples. So this type of data is difficult or really often impossible to analyze qualitatively. You can't just look at this and figure out, and we want to know, like, which samples are most similar to each other. Or maybe just samples from particular categories, like rock types or tectonic settings in this case, tend to group together. But also want to know which variables, like elements in this case, behave in a similar way. And so by knowing these things, we can tell something about the processes that govern the distribution of these samples and their occurrence and their abundances and so forth. So though multivariate data is complex, certainly, there's a way forward for interpreting it. And that is that there's often some degree of covariation between the variables, and this introduces redundancy into the data set. So for example, in the examples below, the lutetium value on the left covaries extremely strongly with the ytterbium value, and same with the yttrium value. So if we know ytterbium, we effectively don't need to know anything else. We don't need to measure or examine lutetium. We just kind of can pretty much guess what it's going to be because of the covariance. So ordination methods take advantage of this redundant information to reduce the number of dimensions, which allows us to visualize and interpret the patterns more easily. So the goals of ordination are basically data analysis, classification, visualization, simplifying the data to aid in interpreting multivariate data, looking for gradients or patterns. I'll explain in more detail, but basically the method essentially creates a new coordinate system by rotating the original data. This allows us to focus on a reduced number of important dimensions. And so those dimensions are synthetic variables, and they represent linear combinations of the original variable. So in this example here, axis 1 corresponds largely to changes in pH and bicarbonate. So I'll explain what these arrows mean towards the end. So the main premise is that the differences between samples, or between sites or whatever, reflect underlying processes, and those samples can be arranged along gradients in those processes. So the process itself might not be measurable or observable. This is probably especially true in the deep time rock record or a lot of the geological observations we might have. But we could try to assess that gradient indirectly from the composition of the samples themselves. So this is using ordination for something called indirect gradient analysis. So for example, if we measure the chemistry in a bunch of different lakes, we may be able to determine that an urban versus rural gradient is the most important control on their chemistry and so forth. So there are a variety of types of ordination, different strengths and weaknesses. They're applicable in different circumstances with different types of data. This table lists some of the major ones. They're grouped in two ways. First, by how they measure distance between points, and then second, by how they determine the new axes that we use for data rotation. So some methods allow you to choose the measure that you're going to use for distance. You can choose one that might be appropriate for your particular type of data. But others use a predefined and fixed distance measures. So principal component analysis uses Euclidean distance between the points, as you'll see. And PCA also determines the new axes through a process called eigenanalysis, which uses the eigenvectors of a matrix. Other methods can use a more iterative trial and error type non-parametric method. And so I'll discuss non-metric multidimensional scaling in the next video, but the other two examples listed here we're not going to cover in this class. Okay, so given that some of the variables are going to covary, perhaps quite strongly, how does PCA help us reduce the data and display the information in fewer dimensions? Well, I'll give a sort of a simple graphical illustration first and then explain in more detail how this process is achieved. So basically, PCA finds the direction of maximum variance through the multidimensional cloud of points. I'm showing a two-dimensional example here for sort of simplicity. That axis is called principal component 1. It's a linear combination of our original variables that explains the maximum amount of variance in the multivariate space. So the points are then rotated such that PC1 becomes the horizontal axis. The remaining principal component axes are orthogonal or perpendicular to all the previous principal components and are ordered by decreasing variance explained. So PC2 explains the second largest amount of variability in the original data, PC3 is the third, and so forth, depending on however many variables you have in your original data set. I'm showing you this in two dimensions. It's fairly easy to visualize the direction that's perpendicular to PC1, but it works in multidimensional space as well. Okay, so one way to describe the structure of the data, the relationship among the variables, is with this variance-covariance matrix. So it gives the variance of each measurement as the diagonals in bold in the example here, and the covariance between all the pairs of variables. So this particular matrix, like all matrices, has properties called eigenvectors. And you may remember from the previous videos that vectors can be used to describe directions in coordinate space. So I explained eigenvectors in more detail in the previous Mahalanobis distance video, so I won't go into them anymore here. It's not that important, but just remember that matrices have these things called eigenvectors. The important thing really is that the first eigenvector defines a direction in space, and the line along that direction turns out to be the direction of greatest variance through our multidimensional cloud of points. So the first eigenvector is the first principal component in our new coordinate system. So we're going to use the eigenvectors. There's going to be a second one and a third one, and however many more you have for the original number of variables. We'll use these eigenvectors as axes in our new coordinate system. and then rotate the multivariate data so that the first eigenvector becomes the first axis in PCA space. The second eigenvector is perpendicular to the first one and explains the second largest amount of variance. So it becomes principal component 2. And all subsequent eigenvectors are perpendicular to the previous ones, and each one explains successively less of the original variability. So each eigenvector, or principal component as we can call them here, has something called an eigenvalue. I explained what that was in the Mahalonovas distance video as well, but in this situation, the eigenvalue measures the amount of variance along that axis. So as I said in the previous slide, the eigenvectors are ordered in terms of decreasing variance explained. So in the example here, what you can see is that the total of the three eigenvalues, given the Greek letter lambda, is the same as the sum of the three original variances. So we can basically say that each principal component axis, each eigenvector, explains a certain proportion of the original variance, and that proportion is given by its eigenvalue. So using the eigenvectors as our new coordinate system, we can rotate the data such that principal component 1 is telling us and reflecting the most important direction of variability. In the example here, PC1 explains essentially all the variance, which is really unusual, but that's because I chose sort of an example case which had extremely unequal variances. But regardless, principal component 1 in your data will almost certainly explain less variance than this, but it still is going to represent what is probably the most important underlying process that causes this gradient of samples. So the axes are, the principal component axes now are linear combinations of the original variable due to the rotation of the points. So we rotate the points into this new coordinate system. So the contribution of each original variable to a particular axis is indicated by an arrow on the plot called a loading. So the loadings are essentially the correlation between the original variable and the axis. So they indicate the direction and the magnitude in the increase in that variable. So a longer arrow indicates a stronger correlation. That means that the variable is more important in controlling or in explaining the difference between the samples along that axis. So to illustrate how that works, in this example here, I've color-coded each point by its yttrium content in the diagram. So the loading, you can see, is a fairly long arrow pointing straight to the right along axis 1, and the colors indicate, in fact, that points on the very left-hand end of axis 1 do have very small values, and points on the right-hand end of axis 1 have large values. And this is what the arrow is telling us. It says, on axis 1, from left to right, the yttrium content increases in the samples. So the example that I demonstrated used the eigenvectors of the variance-covariance matrix. But that's not the only way, and it probably wasn't the best way for the example that I used either. In fact, the choice of association matrix is a very important decision that you have to make. So the other option is to use the eigenvectors of the correlation matrix. So just to compare these two, the covariance matrix centers each variable on the mean, but the scale of the variable still matters. Variables that originally had really high variance will control the resulting PCA plot much more strongly. Variables that originally had very tiny variance are going to be completely unimportant. So you should only use the covariance matrix when all of your variables are measured in comparable units, and the differences between their original variances are meaningful, and you care about that, and you want to use that for interpretation. So the correlation matrix uses a matrix of Pearson's correlation coefficients. And if you remember way back to the lecture on correlation, this has the effect of standardizing each variable so that each one has a variance of 1. So what this is best in the case when you want to remove any effect of different variances, and you would pretty much use the correlation matrix if your variables are measured in different units, because if they're measured in different units, their variance and the differences between their variances are going to be unimportant. So PCA just rotates the axes to this new coordinate system, but there still are just as many axes as there were in the original data. If you have 10 variables, you get 10 principal components. And so the whole point really, as I've been saying, is to simplify the data for interpretation. So obviously we can't look at all 10, but how many should we look at? So there turn out to be several rules of thumb. One is that you can make this plot here called a scree plot, which shows the proportion of variance explained by each principal component. And there's often a break point somewhere between a steep part of the line and a shallower part of the points. And you can use that break point to be sort of a cutoff. In this case, we might say, well, I'm going to look at the first 6 principal components, or something like that. You can also potentially look at every component that, when you add them up, sum up to some predetermined amount of variance explained. Like say, I'm going to look at all the components that add up to 75% of the variance or 90% of the variance. Or you could also potentially say ignore any component that explains less than 1% of the variance or less than the average variance. But in reality, people typically just look at the first 2 or 3 components. Those are the most important ones. Or you could look at however many you can interpret, right? If you don't know what principal component axis 4 is telling you, if you don't know what that gradient is, there's not a huge amount of point in spending a lot of time interpreting it. So PCA has a couple of really important assumptions. First, because it uses covariance or parametric correlation, Pearson's correlation, depending on the association matrix you use. It's based on the Euclidean distance between points. So in many cases, that's okay, but it might not be appropriate distance measure for certain types of data. And in particular, PCA is not a good method to use for count data. So if you have counts of the abundance of species, or rock types, or minerals, or whatever, counts are not good for PCA generally. And second, the use of either covariance or correlation both assume that there's a linear relationship between the variables, which is again not necessarily appropriate for certain systems. Again, counts of abundance, particularly of species, is an example because those species abundances are not linearly related along these gradients generally. So if the relationships are nonlinear, PCA can produce something called a horseshoe effect, where points along axis 2 are kind of twisted into the shape of sort of a horseshoe relative to axis 1. The problem is you can never tell if your points are deformed or not because you don't know what the true pattern should be. But in any case, there's sort of certain things like abundance counts that you should not use PCA for, but the next video will discuss a more flexible method for ordination, one that specifically can be used if you have data, like abundance count, that don't meet the assumptions for principal components analysis. So that's called non-metric multidimensional scaling, and that's what the next video will focus on. Following on from the discussion of principal component analysis in the previous video, this video introduces another ordination method called non-metric multidimensional scaling. The name is obviously kind of a mouthful, so it's often just called NMDS or MDS. It's more commonly been used in biology, also in paleontology, but there are certainly other examples in earth sciences where this could be a good method to use. So just a recap of ordination methods in general. So ordination is a technique used to simplify multivariate data, reducing it from many dimensions down to just a few important axes. In that way, it's possible to graph the data to recognize and interpret patterns. So the main goal is to recognize gradients that hopefully reflect the underlying geological or physical or chemical or whatever processes. There are a number of types of ordination, and we're not going to cover them all in this class. The last video discussed principal component analysis. In that, it used a fixed distance measure, so it used Euclidean distance between the samples, and it created the new ordination axes from the eigenvectors of an association matrix. And by doing so, it imposes a linear relationship between the samples. So that may not be good for certain cases. In contrast, NMDS allows you to choose any distance measure that might be suited for your data, and it uses an iterative method for creating the ordination results. In that way, it doesn't make any assumptions of a linear relationship. So basically, NMDS arranges the points on the ordination plot in the way that maximizes the rank order correlation between the real-world distances, we could say, and the distances in that ordination space. So basically, you start out with the complete multivariate data set, which has measurements of lots of things, or counts of lots of things. Here I'm using species counts because this method is often used for this sort of data. And so you have these measurements or counts in many different samples. You can choose your own appropriate distance measure, which I'll come back to in a second, and then you calculate this distance of a matrix of distances between each sample or each site. These distances are measured in the full multivariate space. This is like if you measure the distance in all, like in the 12-dimensional cloud of points or the 20-dimensional cloud of points, that's what you would get. So next, the computer places our samples or our sites in ordination space, say in 2 axes, 2 dimensions, or in 3 dimensions, or whatever. And then it calculates the Euclidean distance between all the samples or sites in that 2-dimensional ordination space, or 3-dimensional, or whatever you're using, to get a second distance matrix. So the first distance matrix is in the real full-dimensional space, and it's using the measurement for distance that you chose. And the bottom distance matrix is just in the reduced ordination space, so just in the 2 dimensions or then just in the 3 dimensions, and it uses Euclidean distance between that. So basically then the points are moved around in ordination space until the computer can find the best arrangement, the one that has the highest correlation between the two ranks, or between the rank orders of those 2 distances. So NMDS has some clear benefits for certain types of data. The rank order, or non-metric in its name, approach is very good when you wouldn't expect a linear relationship between the variables. And so that's particularly true when you're dealing with abundance counts, like counts of how many individual animals of a particular species you find at each place. This is what the method was really designed for in the first place. So the ability to choose, again, a distance measure that's specifically designed for your data. So if you have these like counts of species, you might use Bray-Curtis dissimilarity. If you're dealing with like presence, absence for species in different regions, like biogeography, you could use Jacquard coefficient or one of many, many others. We're not really going to get into distance measures beyond this, but there are a million of them perhaps. So this ability is a big plus. But the main downside is that you must choose beforehand whether to perform ordination in 2 dimensions or 3 dimensions or some other dimensionality. And so because the points are optimized in that particular space, the 2D plot and the 3D plot won't look the same. And it's also possible, it's potentially a drawback, that this iterative process may find a solution, sort of like the local best solution, but isn't the best possible solution in all possible choices. This typically isn't too big of a worry with the algorithms that are used these days, but it is a potential drawback. So the method uses this iterative technique, basically trial and error, to find the best arrangement of points in ordination space. And in this case, best is defined by this parameter called stress. It's a measure of the goodness of the fit of the relationship. So the plot here, which is called a Shepherd diagram, shows the distance, or in this case the dissimilarity, on the x-axis, this is the measure of dissimilarity or distance in the full dimensional real-world sense, in our original complete data set. And the y-axis shows the distance as measured in ordination space. So if the fit was perfect, there would be a perfect rank order correlation between the two, so that the points would fall along a continuously increasing or a monotonic line. So monotonic just means that the values either only increase or only decrease. And so the stress is calculated from the residuals of the points, the blue dots, around that monotone regression line, which is the red line. So by definition, stress, which is this mismatch between the ordination fit and the real data, must always decrease as you consider more dimensions. Dimensionality is often given the letter K in this context. And this sort of intuitively makes sense. I mean, if your original data has 5 dimensions, and you do your ordination in 5 dimensions, you can fit it perfectly. You can get a perfect match because you just are using the exact same space. But it's a little bit, it should be pretty good to do it in 4 dimensions, but a little bit harder in 3, and a little bit harder in 2. And when you get to 1 dimension, it's going to be really hard to arrange those points in such a way that you preserve all of the distances among them in the original 5 dimensions. So you're losing progressively more information, so it becomes harder to capture the true relationships. And remember that the 2-dimensional solution is not going to be a projection of the arrangement of points you might get with higher dimensions. So you can't just like say, I'll do it in 5 dimensions and just look at axis 1 and 2, because as we'll see, the axes don't actually mean anything, and that is not the same as if you did it just in 2 dimensions. So given that, how many dimensions do you choose? How do you know what to do? Well, I mean, it's possible, although a little difficult in R, to create a scree plot that shows stress versus number of dimensions. But in practice, people pretty much just do the ordination in 2 or 3 dimensions because it gets a little unwieldy to look at more. But you should, at least if you're doing that, make sure that the fit is somewhat reasonable in the 2 dimensions or the 3 dimensions that you're looking at. So there are some rules of thumb, basically that a stress greater than 0.2 is a fairly poor fit, and there might be some risk of making error when you interpret the relative position between the points. A stress between 0.1 and 0.2 is an okay fit. Maybe some of the distances might be a little bit inaccurate, but overall it's pretty good. And a stress between 0.05 and 1 is said to be quite good, and you should be able to make pretty confident inference about the relative position of the points. And then a stress less than 0.05 is really excellent, but you almost never really see this when you're dealing with complicated data. So the ordination plot looks somewhat similar to other ordination, like principal component analysis. The distance between the samples, your samples or your sites, which are shown here at the colored circles, indicates their relative similarity. So the points that plot close to each other have quite similar composition in terms of the original variables, the measurements or the counts, and points that plot far apart are quite different. So unlike in PCA, the variables, which are the measurements, the measured parameters, or the counts of the items or the species or whatever, are also shown as points, or you're able to do that. And so what this means is that if a variable, which are the little crosses here, I didn't label them all, plots close to a particular sample, that indicates that that sample contains high values of that variable. So in this case, where the variables are species, it tells you which species tend to be more common in which samples or in which groups of samples. So you should use your knowledge and other information about the samples to qualitatively identify gradients in those samples. So in this example, I've color-coded the samples by region, so the red ones and the blue ones come from different places around the world. So you can see kind of a nice separation between the two regions. So basically, you use other information and maybe color code your points, or use different symbols for your points to be able to, sort of qualitatively or visually look for gradients or clustering or separation between these groups that you might know of. Okay, so unlike in PCA, these points, remember, are arranged by this iterative process. So it turns out that the axes don't actually mean anything. Remember, in PCA, the axes correspond to these eigenvectors that explain a particular amount of the variance. So because here the axes really are not that meaningful, you can rotate the plot, you can translate it, so you can shift it from left to right or up and down. You can scale it, so you can enlarge it or you can shrink it, as long as you retain the relative distances. So I said that the axes don't mean anything, but I will note that in R, if you're doing this, what it does is that it actually performs a PCA on your ordination results after they're obtained. So axis 1 is supposed to be the greatest variance in the ordination space. So not the original data, but in ordination space. Okay, so to summarize, I'll just wrap up with a couple suggestions for choosing ordination methods. So if Euclidean distance is appropriate, and if there generally are linear relations between the variables, principal component analysis, or PCA, is often a good one to use. And this applies probably to most types of geological data, especially if you have measurements on a continuous scale. So really, in most cases, PCA is going to be quite a reasonable one to use. If you can rely on a linear relationship, but you maybe want to use a different distance measure, like if you had biogeographic data with presence or absence of species in regions, you could use something called principal coordinate analysis, which we're not going to cover in this class. And so the one case where NMDS is really most widely used is with abundant count data in multiple samples, so especially counts of biological species abundances in different samples. In that case, you really cannot assume a linear relationship, and there are specific distance measures designed for that sort of data types. I've also seen NMDS used for ordination of for example, detrital zircon age spectrum data in the geosciences. So I'd say there probably are more circumstances in our sciences where it could be a good method, but it really has been most widely used in biological sciences to this date. This video introduces maximum likelihood estimation, which is a method for fitting models to data and comparing those models to find the best one. We'll cover this topic in a fairly qualitative way. For more details, there are many good references, particularly the book by Burnham and Anderson on model selection and multi-model inference. So if you really want to know more, particularly about the mathematical end of things, I would definitely recommend that reference. So to introduce the concept of likelihood, let's first think about probability, which you've heard about before in this class. So for probability, we can assume that we know something about the underlying reality, or the true model, or the overall population, for example. We can then ask, what is the chance of observing this particular data, or sample, given that known reality? So for example, if the true population of quartz, or the true proportion of quartz is 0.2, what is the chance, or what is the probability of finding 32% in one particular sample? Or likewise, if grain size has a normal distribution with some known mean, mu, and some known standard deviation, sigma, what is the chance, or what is the probability, of observing some set of data, x? Likelihood is just the reverse process. So for likelihood, we want to ask, given some observed data, what is the chance that a given reality or a given model is true? So thinking about this in the reverse way, if we counted 32% quartz grains in a sample, what is the chance, or what is the likelihood, that the true proportion is 0.2? Or if we observe some data x, what are the best normal distribution parameters, mu for the mean and sigma for the standard deviation, to describe that distribution? So that's likelihood. So maximum likelihood estimation has two goals. First, it determines the best model parameters, the most likely reality that fits a given set of data. So this is the likelihood part. We want to find the most likely parameters, the most likely reality or model for the given set of data. And second, it's typically used to compare multiple models to determine which of those is the most likely explanation or the best fit for the data. To do that, it maximizes something called the log likelihood function to estimate the model parameters, and then uses concepts from information theory to compare the model fits. So I'll discuss each of these steps in a bit more detail, starting with the likelihood function. So let's take an example. Let's say we have some data like this histogram here, or they're like asteroid sizes or something like that. We maybe want to know if it's best fit by a statistical distribution A or a statistical distribution B. And so I'm not going to cover distributions in this course, but so there's a lot of them. Different ones apply in different circumstances. So basically, by fitting a particular distribution and knowing that a particular distribution is the best fit for this data, we can learn something about the underlying processes. Okay, so if we start by thinking about probability. Let's say we assume that we know the distribution. We can describe the probability of observing the data. So this function here is the way that you read these sort of things with this conditional probability is that it's the probability of observing the data, x1, x2, and so forth, given that they come from a distribution with parameters theta. So the vertical bar between the x's and the theta basically means that the probability of observing the x's is conditional upon the theta being true. So given the way that conditional probabilities work, we can also treat this as the probability of observing x1 given the parameters, multiplied by the probability of observing x2 conditional upon those parameters, and so forth. So in other words, we get the product, that capital Pi symbol, of the probability of observing each data point given the parameters. But remember that likelihood is just the reverse of probability. So to get our likelihood function, we can define it this way. So this equation here states that the likelihood of the true parameters being some values theta, given the observed data x, is the same thing, or is equal to, the probability of observing the data x, given some true parameter values. So what we want to do is we want to find the most likely parameter values given the data, but it turns out that maximizing the likelihood function is difficult. So what we're going to do is we're going to maximize the log likelihood function instead. And so by taking the logarithm, we can get rid of the product symbol, capital Pi or big pi there, and instead use a sum. So we're basically just going to get the log likelihood, so that log L, so that the likelihood of the parameters being true given the data is the same thing as the sum of the log probabilities of the data being true given the parameters. So the graph here shows the log likelihood, blue or lower values, red or higher values for likelihood, and it's determined at each point in the graph by calculating the probability of observing the data given that particular mean and standard deviation. So we can say, okay, if the mean was 1 and the standard deviation is 0.2, what is the probability of observing the data? And that's our likelihood for those parameters being true. And then we can say, okay, let's say the mean is 1.1 and the standard deviation is 0.2. What's the probability of observing the data? And that's our likelihood for that point. So the black dot shows the mean and standard deviation that you would calculate from the actual data. It's also the maximum likelihood estimation point of this likelihood function too. So the maximum likelihood parameter estimate is exactly what you would calculate if you just used the raw actual data. So you might be wondering at this point, like, what is the point of all this? Like, you know, if we can just get this value from the data, why do we need to go through this whole process about finding the likelihood function and maximizing it and so forth? Well, the real strength of this method is the ability to compare multiple models to find the one that is most likely of those given the data. Right, so the maximum likelihood estimate is basically what you would just calculate from the raw data anyways, but to be able to compare them, we need to use information theory methods, which are fairly complicated, so I'll describe them in general terms. Okay, so there's something in information theory called the Kullback-Leibler information. And it basically just quantifies the amount of information lost when some probability density function, which we'll call G, is used to approximate model F, and F is also some probability distribution function. So this is the equation that they give for this. Model G is evaluated over some parameter space theta, and then the function is integrated for continuous distributions at least over x. So the details of this integral function aren't critical because it actually isn't going to be used. More generally, we actually really want to know which of our candidate models that we're looking at best describes the underlying truth, what's often called full reality. So F is actually full reality, it's not a model. And G is one of our models. We're comparing multiple models to see how well they approximate full reality, basically figuring out which one loses the least information when you're approximating reality. So full reality is, of course, not knowable. So in practice, this equation is rewritten into a form so that full reality becomes a constant and drops out of the equation. I always find that kind of an amusing phrasing because it's you know, reality is removed as a constant and you get this equation. But basically then by turning this into sort of a relative form, the models can be chosen on the basis of their relative distance from full reality. Okay, but the Kullback-Leibler information turns out to be extremely difficult to calculate, even in a relative sense, for many different functions. But Japanese statistician Hirochugu Akaike showed that you could actually estimate this KL information from the maximum log likelihood. And so he created a value which he called an information criterion, or AIC, and which is now called the Akaike information criterion. So AIC is based on the maximum log likelihood in blue there. Theta with a little hat on it means that this is the maximum likelihood estimation point. That's the sort of the best parameters for that particular model. And he also incorporated the number of parameters, so the number of variables that you're using to fit this model, which he gave as K, or which is in red here. And so in this formulation here, smaller AIC values indicate a better fitting model because they have higher likelihood likelihood is multiplied by minus 2, so bigger likelihood or bigger log likelihood gives you smaller AIC in the way this equation is written. So the K term then is often said to penalize more complex models, that is, models that have more parameters. So adding more parameters always increases the model fit and always gives you a higher log likelihood. However, more parameters also increase the uncertainty in the model prediction, for example, because each parameter must itself be estimated from the data. And so therefore there's some error on each estimate, and if you're making lots of estimates, you end up with lots more error on the overall fit of the model. So basically AIC is a trade-off between bias. So like, is the model biased towards being lower or higher? So bias is reduced when you have more parameters, as the model should be a better fit. So that's a trade-off between bias and variance or uncertainty. Variance is increased with more parameters because there's more sources of uncertainty. You have to fit more variables as you're doing your model. So relative differences between the AIC values for a variety of different models can be used to determine the best model of those candidates that you're looking at. But you can also convert the AIC values into something called Akaike weights, and they basically indicate the proportional support for each model. They'll sum up to 1 or to 100%. So in the example that I introduced at the beginning as sort of our test case here, model A, which is the log normal incidentally, is the best model of the two. It has an Akaike weight of 0.72. So notice that those two models sum up to 1. So one gets 72% of the support, as we'll call it, and one gets 28%. So this gives, relatively strong support for model A over model B, but there's no definitive cutoff in this sort of approach here. This is exploratory statistics, and so you need to use your judgment to determine, if this is really strong support for model A, or maybe it's not. Maybe you're not as confident that A is better than B. Okay, so just to end with some warnings when you're performing model selection and using AIC. So both the likelihood values, the maximum likelihood values, log L, and the AIC values are only relevant when you're comparing them among models run on the same data. So you can't compare AIC on one data set to AIC on a different data set. It's just fundamentally not meaningful because the absolute AIC value is not important. The reason for this ultimately is that Kullback-Leibler distance or information is measured in a relative sense, and so because it's relative, the actual AIC value is not comparable across different data sets. Also, and this is quite important, to be aware that AIC is only telling you which of the models is the best candidate of the ones you used. So if you perform model selection on 4 separate models, it will happily tell you that one of those models is the best. But that doesn't actually mean that that model is itself necessarily good. It's just the best of the ones that you looked at. And so if you happen to choose 4 models that are all bad models, it'll tell you which one of those is the best bad model, but it might not be good in an absolute sense. And finally, don't combine model selection with hypothesis testing. So if you use model selection to figure out which combination of variables, for example, is the best explanation for your distribution, you shouldn't then do hypothesis testing and get a p-value, because the significance that you would get will be inflated. You're examining multiple models and choosing the best, and that's the same thing as testing multiple hypotheses and reporting only the most significant, and you should never do that. So model selection and AIC are exploratory methods, which are valid methods to use, but you should never mix these exploratory with hypothesis testing approaches.
An insurance company determines vehicle insurance premiums based on known risk factors and then charges accordingly. And interestingly, one of those factors is the color of your car. The insurance company believes that people with some color cars are more likely to get into accidents. And so to research this, they examine police reports for total loss collisions, and they find this data. And so this is what's called a frequency table. And we're working here with categorical data, or in other words, qualitative data that is categories, but it's not numerical data. And so this frequency table tells me that there were 25 reports that involved a blue car. And so from this large collection of reports, the frequency or the count of reports for each of these colors was recorded. And that's what a frequency table is. And so the first thing we're going to do is try to create a graphical representation of this data. And first one we're going to do is called a bar graph. A bar graph is reasonably simple. The idea is we have a horizontal and our vertical axis. And along the vertical is going to be our frequency. Actually, let me write this a little differently. I'm going to actually try to write it sideways here. Frequency. I didn't write that very well. Okay, and then we're going to create bars for each of our colors. So this vertical axis is going to be an actual numerical axis, and it's going to have to go up at least past 50 in order for me to be able to fit all this data in. So I think I'm going to go 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, and then I'm going to need to go at least one more, so there's 55. And I'll go ahead and toss 60 in here. So now we can draw a bar for each of our colors. So our blue cars have a frequency of 25, so I'm going to draw a bar, and that bar is going to have a height of 25, right? And so this is going to correspond to blue cars. So now I'm going to draw a bar for green cars, and it needs to have a height of 52, which is right around here. And I'm just sort of estimating here. Typically, software packages like Excel is a common one, or even something like Google Docs is used to create these graphs rather than trying to draw them by hand. But for the sake of illustration here, we'll go ahead and we'll try to draw this by hand. And so there's our red cars, which have a height of 41. And then you would continue this on for the other colors. And our resulting bar graph will look something like this. Now, you can tell that it's kind of hard to tell where the where the bars are here. And so one solution to that would be to put in grid lines, which would look something like that. And put those every 5 or 10 spaces. So that'd be one option. Ooh, I did not mean to do that. Hold on, there we are. So that would be one option for dealing with the for dealing with this issue. There we go. Good enough. Another option, and probably a little simpler, would be to just put at the top of each bar what the corresponding frequency is, and that way somebody reading the graph could easily identify the frequency of each of the bars without having to look horizontally. Now, the advantage of the graphical display, of course, is that it makes it very clear visually what the relative sizes of these quantities are. And so this would be a bar graph for categorical data. So this was a bar graph for this frequency table of car colors. So now we're going to try to create something called a Pareto chart. Now, a Pareto chart is really the same idea as a bar graph. It's just a specific type of bar graph. So we're going to start it the same way. 5, 10, 15, 20, 25, 30, 35, 40. Now, of course, if I really wanted to do a really high-quality graph, I would not just be freehanding this. I would be using some either graph paper or use a pencil, or, like I said, use a computer. But this will be okay for now. So the idea of a Pareto chart is that we're going to do a bar graph, but we're going to arrange the bars in decreasing frequency order. So in other words, we're going to put first, the first color we're going to draw, or sorry, the first bar we're going to draw is for the category with the highest frequency, which is 52 here for the green cars. So that's our green cars. And then our next highest frequency appears to be the red cars with a frequency of 41. And so we could draw in our red car bar. And then next one is our black cars with a frequency of 39. And so on. And there's our completed Pareto chart. Now, the advantage of a Pareto chart over our original bar graph is that here, at least without the numbers listed, it would have been hard to tell the difference between, say, the red cars and the black cars. But by creating a Pareto chart, you can, the bars that are similar height are going to be right next to each other, and so it's easier to see the difference between the heights. So, sometimes we're interested in not so much the size of each of these categories, but rather their relative sizes. And so we're going to talk about relative frequencies, and then try to create a pie chart. So first thing we're going to do is talk about relative frequencies. And so this would be computing the percentage of all cars that fit into each of these categories. And so first thing we need to do is add up our total frequencies. So let's see, if I pull out my calculator and add these up, I get 216 is the total number of reports that were read. And so the relative frequency is what is the percentage. So 25 out of 216. So that would be 25 divided by 216 comes out to be about 0.1157. Or about 11.6%. So that means 11.6% of all of these reports were blue cars. We could do the same thing here for green cars. 52 out of 216 is about 0.2407, or about 24.1%. And we could find the relative frequencies for all of these colors. So I'm going to do that real quick. And there's all of our relative frequencies. So the idea of a pie chart now is that we're going to create a graph where we have a circle that we're going to divide up into pie slices. And so the idea is that the size of a pie slice should correspond to the relative percentage. So for example, if I saw a slice like this, that looks like it's about a quarter of the circle, so that should be about 25%. Now, if you're getting really technical here, and want to very precisely create a pie chart, you can take each of these percentages and multiply it times 360 degrees. Well, of course, you would need to convert the percentage into a decimal first. And if you do that, you would come up with a number of, it's about 38 degrees. And then you could use a protractor to come up with the graph. But the reality is that most of the time people don't bother doing that anymore because, we usually use computers nowadays to create pie charts. But just for the fun of it, let's see if we can freehand one pretty close. So I'm going to start with the green here, because 24% is awfully close to 25%. So I would expect that to be just slightly less than a quarter circle. So that's my green, which is, 24%, not 24.1%. Okay, so let's maybe go to red now, because red is going to be 19%. And so that's going to be even less than 25%, right? Let's see here. If I divide this into 5 pieces, each one would be another 5%, so it needs to be about 1/5 less than that. Okay, so maybe like that. Let's call that red, and that's about 19%. And then white is going to be 18%, so that's going to be even a little bit less than that one. That's pretty good. I know that's not white, but white wouldn't show up not very well now, would it? And so we got about 16.7% there. And black is going to be similar, but a little bit bigger than white, a little less than red. So maybe right around there. So we'll call that black, and that one's 18.1%. And now we have blue and gray left, both of which are going to be, let's see here, gray is going to be about half of that one. So, let's go with that. So there's blue, 11.6%, and then we got gray here with 10.6%. Now this is a pretty lousy pie chart. Like I said, we'd be a lot better off using a computer, but at least you get the idea of how we form a pie chart by hand. The idea is we want the relative proportions, percentages of the circle, to correspond with the relative frequencies of our data. So here's a slightly nicer looking pie chart that shows the percentage of voters supporting each candidate running for a local Senate seat. So we can see here that Douglas has 43% of the voter support, Reeves has 11%, and Ellison 46%. So if there were 20,000 voters in the district, about how many voters would be supporting Reeves? So to answer this question, we're going to use our percentages here to help us out. This is telling me that 11% of voters are supporting Reeves. So to find 11%, so we want 11% of the 20,000 voters, we just need to multiply 20,000 times 11% written as a decimal. So we're finding 11% of 20,000, which is about 2,200 voters. So it's really easy on a computer to do all kinds of cool graphics, graphical displays, but that doesn't always mean that you should. So we're going to take a minute and talk about some bad graphical representations of data. So here is the car color data we were looking at earlier, and here it's done in a 3D bar graph. The problem with this graph is that because of the perspective of it, it's almost impossible to read now. I mean, it's really hard to tell which of these bars is actually larger when it is on this slant like this. And so this is really a bad graphical representation now. It's really hard to read. Now here's another situation. So suppose a labor union produces this graphic designed to show the difference between the average manager salary and the average worker salary. Now, it could be, I mean, if I was to look at this, I'd say, okay, if I was to imagine this as, you know, the worker salary, then let's see here, that, ooh, wow, this one's like 4 of those. And so if I was to look at this, I might think that, wow, those manager salaries are 4 times bigger than the worker salaries. But it's sometimes hard to tell because not everyone, you know, does things that way. It could be that the manager's salaries are only twice as big as the worker's salaries, and the you know, the person creating this representation said, "Oh, look, it's only twice as big," right? And so that visual distortion of area versus a length really makes this hard to tell based on the graphic what's really going on. So this type of pictogram is not a good representation. Now there are some representations where, say, you would use like some kind of picture, like a $sign to represent money, and then you use a certain number of them to represent relative sizes, and that's a lot more acceptable because then it really is the length of the picture that corresponds with the quantities. Let's look at one more, and this is a big problem with bar graphs. Notice these 2 graphs here. These are 2 graphs from a poll about same-sex marriage rights taken in December 2008. And they look quite different, right? Which of these is misleading? The one that's misleading is this one. This is a bad graph. It's a bad graph because this vertical axis is condensed. It's condensed from 40 to 60, and so it creates a misleadingly large disparity, right? This bar now looks 3 times bigger than this bar, whereas if we actually look at it measured from 0, we can see that the difference is much smaller than this graphic would lead us to believe. So a teacher records scores on a 20-point quiz for 30 students in his class, and the scores are shown here. Let's try to create a frequency table for this data. And so we're going to create a chart, and we're going to have our data value and our frequency data. Now, this is no longer qualitative data, but it's now quantitative data, right? Because we're looking at numbers. But we're still going to treat it similarly. We're going to look at each score as our data, and then the frequency of that corresponding score. So maybe I'll even change this to say score. So for example, a score of 0. Looks like we've got 2 of those. How about a score of 5? Looks like we only have 1 of those. Kind of want to do this from smallest to biggest. So what's my next smallest number? Oh, looks like I got a 12 here, and I've got 1 of those. And then, let's see, next smallest. I've got a 15 here and another one there, so it looks like I've got 2 15s. And I would go down the line doing the same thing for each of the possible scores, and the resulting table would end up looking something like this. Now, it might be nice to create a graphical representation of our data. And so one option would be to try to create a bar graph like we did before, and that one might end up looking something like this. But this is somewhat misleading because these are numerical data, it's kind of weird to have 0 and 5 here and like 19 and 20 here. These are 5 apart, and these are only 1 apart. And so this isn't the best representation for this type of data. And so for that, we're going to need something called a histogram. Now, a histogram is very similar to a bar graph in that we're going to have, again, frequency along the vertical. I'm just going to write it up here because there, frequency along the vertical. We can see here we're going to need to go up to 8. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We'll do that. The difference is now the horizontal axis is also going to be a number line. So we have scores ranging from 0 to 20 here. So we'll go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And of course, that should be nice and evenly spaced. And so now, for each of our score, we're going to create a bar. And when we create a bar, the value on the left side of the bar is included, but we're not including the value on the right side. So for example, for a score of 0, our bar will start at 0 and go up to 1. And so this is really a bar corresponding to a score of 0 here, which is on the left side of the bar. Different books and different software does this differently, but this is the approach that we're going to use. And so our next score here has a frequency of 1, but it has a score of 5. So it's way over here. There's a big empty space here in our graph corresponding to all those scores that never, didn't show up. Our next is a score of 12, also with a frequency of 1. And then we've got a score of 15 with a frequency of 2. And then a score of 16 with a frequency of 2. So this is going to start at 16 and extend up to, but not quite including 17. And then at 17, we're going to have a bar of height 4. And then 18, we're going to have a bar of height 8. It's about 8. And then at 19, we're going to have a score of 4. And notice that because we start at the value that's on the left, our score of 20 here with a height of 6 is actually going to start at 20 and go up to 21, even though we don't actually have any scores at 21, because this bar includes values starting at 20. And this is our corresponding histogram. Notice that we get a better idea of the overall layout of the data from this than we did from the bar graph. Now, suppose we've collected a lot of data, like 100 men's weights, as part of a nutrition study, and they range in value from 121 to a high of 263 for a total span of 142. And these scores might be all over the place, so we might have 100 different weights. And if we tried to create a frequency table for showing each individual weight and the frequency, we'd probably get a lot of frequencies of 1. In fact, almost all of our values would probably have a frequency of 1. And so what we're going to do is group the data into something called classes, or class intervals. And so this is going to be a range of values, and then we can create a frequency table based on the range of values. And so there's a lot of sort of decisions we have to make here, one of which is how many classes we want to have. And usually we want somewhere in the range of 5 to 20 classes, or groupings, depending upon sort of how much data we have or how big the data set is. And then oftentimes it's nice to have the ranges sort of start at nice values, though that's not necessary. But it is important that each interval be the same size. And so we could say, with our 142 values here, we would have a lot of options. Let's consider a couple. So, for example, I could have, let's see. So, I mean, like one option would be if I used 10 classes. Actually, let's do 14 classes. Then the width of each one would be around 10. So I could create a class like 100 to 129, and 130 to 139, and I'd end up with 14 classes that way. And so that'd be one option. I think I'm going to go for a slightly different approach here, and I'm going to make my classes a little wider. I'm going to use a class width of 15. So I'm going to start at 120, even though my data starts at 121, just because it's a nice number. And so my first class interval will be 120 to 134. My next one will start at the next value up, so 135 up to 149. Just as a point of clarification, if my data included decimals, like if people reported their weights as like 135 and a half, then this class would need to go all the way up to like 134.99 in order to cover those decimals. But we're going to assume, for the simplicity for now, that's not the case. And so my classes would continue developing something like this. So here's the rest of our class intervals, and then I put in some frequencies. Of course, this would come from the actual data. This would tell us that 4 students' weights were in the range of 120 to 134, and 14 students' weights were in this interval. And now that we have this, we can create our histogram. So our histogram here would start at, let's say, 120, and then maybe 135 and 150 and 165 and so on and so forth. And so our first bar here would have a height of 4, and would start at 120 and go up to, but not include, well, again, not include, so it goes up to 135, because we're going up to 135. My next category would have a height of 14, which I don't think I left enough room here for, so we'll just pretend 14, and extend out to 150. Right, so it's including this entire range of values. Let me show you what this is supposed to look like. This is what that histogram would end up looking like, and this very nicely shows the distribution of weights. Now, some software doesn't let you put the values along the axis like this, and if that's the case, you can create a bar graph where the title of the bar is the range of values, and that does a pretty good job at capturing the same idea. If we have a set of class intervals and frequencies like we had for our weight data, one option for representing that was the histogram that we created. Another option would be to create a pie chart. We could do that by, again, calculating out relative frequencies. and these would be percentages, so we'd have to add our total number of frequencies and divide each of these by that to find a corresponding percentage. And then we could use that to create a pie chart. And that pie chart would end up looking something like this. And as you can tell, this is really hard to read, right? I mean, even if we were to put these labels directly on the pie chart, this is probably not a particularly useful representation of the data, certainly not in comparison to, say, our histogram that we had earlier. And so, when you have a large number of categories or classes, doing pie charts is probably not the best idea. So sometimes we need to compare two different groups of data. And so, for example, this data comes from a task in which the goal is to move a computer mouse to a target on the screen as fast as possible. So you have to move the mouse and click on a target. And it was done twice with a small rectangle and a large rectangle, so for two different targets. And we've collected frequency data, and we've created class intervals, each of width 100 milliseconds. And so this is our data. And so to create a graphical representation, one option would be to create histograms of each of these data on top of each other. This is called a comparative histogram. And it would look something like this. Now, this particular graph is done as a bar graph, where the class intervals are the bar labels. And that's mainly because of the limitations of the software I was using. But you can see that the lighter blue here is representing the times for the small target, and the darker reddish color, purple color, is showing the times for the large target. And we can start analyzing the behaviors here using a graph like this. For example, we can tell that the large target scores seem to sort of on average be smaller, and that they tend to be more clustered, whereas the small target scores tend to appear to be more spread out. Now, this is still not a great representation of the data, and so another option here would be something called a frequency polygon, frequency polygon. And the idea is basically the same, except we put a dot at each interval, basically at the same height that the histogram would be. And then we sort of connect the dots. Now, this is a little misleading because we're not suggesting that this actually, increases that way, but it gets the idea of trend perhaps a little bit more than the histogram does, and this is what that ends up looking like. Now, this again sort of gets that idea that the large target values are a little smaller, and a little more compact, whereas the small target scores are a little more spread out and appear to be slightly larger. So next we're going to talk about numerical summaries of data, and we're going to look at a few of them. First, we're going to start with measures of what's called measures of center. Now, you may have heard of averages before, and we try to avoid to use the word average in statistics because it's a bit ambiguous. And instead, we're going to use the word mean, the arithmetic mean, more specifically, which is what we're going to use to calculate what you've probably heard called average before. And so the mean we calculate by finding the sum of the scores and dividing by the number of scores. So the mean is simply this, sum of scores. So there's our sum of scores, and we're going to divide it by the number of scores. We have 4 scores here. And pulling out my calculator, I get 85.25. So we can say that Marcy's mean exam score is 85.25. Let's look at another one. Here's the number of touchdown passes thrown by each of the 31 teams in the National Football League in the 2000 season. And we could find the mean number of passes thrown. So if we're going to do that, we're going to need to add all of these up. So we're going to find this plus that plus that plus that plus that plus that, so on and so forth, And it turns out those add up to 634. Then to find the mean, we're going to take that sum and divide it by how many scores there are. There's 31 different counts here. And we divide that and we get 20.4516. Now, it would be appropriate here, because all of this data has no decimal places attached to it, it would be appropriate here for us to round this to 1 decimal place. It's common to round means to 1 decimal place more than the data originally had. So it would be most correct here for us to say the mean number of touchdown passes thrown in the NFL season in the 2000 season was 20.5 passes. But it's certainly not uncommon to hear the word average used in place of mean, at least in common language. So in addition to the mean, another measure of center is called the median, and we'll get to the actual question here in a second. So the median is the middle value from a set of data. And so, for example, middle value in order. So if we list our data in order, the median will be the middle value. So if my data was 1, 3, 7, 10, 15, the middle value would be 7. 7 would be the median of that data. If my data was 1, 3, 7, 8, 10, 15, notice now the middle is right between 2 values. And so when that happens, we find the mean of those 2 values. In other words, we add them up and divide by 2, and we get 7.5 as the median. So if we have an odd number of data, then the median will be fairly easy to find. It will be in the middle. And if we have an even number of data, then we're going to need to split the difference. Now, the way that we can find where the median is using something called a locator. And so we're going to take the number of data. In this case, we had 5 pieces of data, and we're going to divide it in half. So 5 divided by 2 is 2.5. Now, if this number comes out to be not a whole number, which will happen whenever we have an odd number of data, then we go up to the next whole number up. So it's going to be the third piece of data. Third piece of data, right? So in our order, 1, 2, 3, third piece of data. In this case, 6 divided by 2 is 3. And so this already is a whole number. When that happens, then we find the mean of, in this case, the third and fourth. So we start at the third value. So we find the mean of the third and fourth pieces of data. But for small sets of data, you can use this visual approach, which usually works pretty well. So here we have a set of data. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 pieces of data. So we use the letter n to represent the number of data. And so this is the even case, right? So I can say 10 divided by 2 is 5. And so we're going to need the mean of the 5th and 6th data values here. But most importantly, we first need to put our data in order from smallest to biggest. Or biggest to smallest, doesn't really matter, but I'm going to go small to big here. So we got 2, 4, 5, 5, 6, 7, 7, 8, 8, 10. Let me double check I got everything. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 pieces of data. Good. And really you can see that this point here splits the data in half. This is the 1, 2, 3, 4, 5th piece of data. So the 5th and the 6th piece of data here we need to find the mean of. 6 plus 7 divided by 2 is 6.5. And so that is our median of this data. So let's look at another example. So here is a set of touchdown passes, and this time they've been arranged in order for us, which is awfully nice. And so notice there are 31 pieces of data. If I divide 31 by 2, I get 15.5, which is a decimal value, and so I go up to 16th data value. Right? Because we have an odd number of data, we know that the median is going to be a single value. So now I can just find the 16th piece of data, because it's already listed in order. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So my median is 20. So here again is our income data from 100 families. We have income and frequencies here, so we're working off of a frequency table. So we have here 100 pieces of data. So that's even, so we know that the median will be in between the, in this case, 50th and 51st piece of data. Sorry, piece of data. Okay, so between the 50th and 51st piece of data. So now we need to figure out where that is. So our first 6 pieces of data are here. So we've counted up 6 pieces of data so far. And then we have another 8 pieces of data here. So altogether, that would be 6 pieces of data there, 8 pieces of data there. We've now counted up to 14. So together, these make 14 pieces of data. So we have 14 pieces, and then we add in 11 more, and now we have a total of 25 pieces of data. So all of these together is 25 pieces of data. And then let's see, if we add in another 17, that's going to get us up to, let's see, 42. And so altogether, this is 42 pieces of data. And then add that to 19, and that gets us up to 61. And so altogether, this is 61 pieces of data. So now that we're up to 61, we've passed 50 and 51, which means where were pieces of data 50 and 51? Well, they weren't here. They weren't up to 30, which means pieces of data 50 and 51 must have been here. And so both the 50th and 51st pieces of data were 35,000, and the mean of 35,000 and 35,000 is also 35,000. And so here the median income in this neighborhood is 35,000. Now, interestingly, look what happens when we add another family. So we're going to add another family to our mix here. Again, we're going to add this family who makes $5 million a year. So now we have 101 families, and from that we know that the median is going to be a single value, in this case the 51st value. And just like we did before, we can start counting up from the bottom. And since the bottom part of the data didn't change, we already know that the 51st piece of data is in this category, and so the 51st piece of data is 35,000. So notice that with the median median income in this neighborhood has not changed with the addition of this very rich family. So this is one of the features of the median, is that it is not swayed by outliers nearly as much as the mean is. When we have quantitative data, numerical data, we usually find the mean or the median of the data. That's usually the most useful measure of center. However, when we have categorical data, like these car colors with corresponding frequencies, then finding numerical measures isn't possible. And so for that, we have something called the mode. The mode is another measure of center, and it is a measure of the most typical value in the set. In other words, it's the value that shows up the most often. And for that, we simply look at our frequencies here and say, that's my biggest frequency. And so the mode here is green. Green is the color that shows up the most often. So consider these 4 sets of quiz scores from 4 different sections of a class. A quick calculation will discover that the mean and the median of each of these data sets is 5. And yet, looking at them, you can tell that they're quite different. And so for this, we're going to need to talk about not measures of center. In this case, they all have the same measures of center. But instead, we're going to need to talk about how spread out or how varied the data is. And so we're going to talk about a range of measures, the first of which is called the range. And the range simply measures the difference between the biggest value and the smallest value. So it tells you how much the data ranges over the entire set of data. So here, my largest value is 5, my smallest value is 5, which means this data has a range of 0. And that's really important, because that tells me that the data is all the same. This data has a range of 10, right? It ranges from 0 to 10. And so that means it is quite spread out from its smallest value to its largest value. Let's see here. This data ranges from 4 to 6, and so the range here is 2. And this seems to be capturing pretty well how spread out the data is, until we look at this last set where the range is also 10. But if we look at this data set and this data set, we can see that they're quite different. This set, half the class failed and half the class got perfect, whereas in this class, we had 1 failure, 1 perfect score, and a lot of people right in the middle. And so, while the range is a useful measure of center, we would eventually like to have a different measure, or a more specified measure that looks a little deeper than just the range of values. So next, we're going to look at a different measure of spread called the standard deviation. And so we're going to be measuring deviation or difference from the mean. And so the first thing we're going to need here is the mean of these scores. And the mean of these scores turns out to be 5. And so what we're going to do here is look at our data and then the deviation. In other words, the difference between the data and the mean. How far each of my data values is from the mean. So for this data set here, let's see, we got 0, 0, 0, 0, 0, 10, 10, 10, 10, 10. So the deviation here is data minus mean is -5. And I think you can trust me that all these other zeros are going to be the same. And then for the 10, 10 minus 5 is 10 minus 5 is also 5, positive 5, and so on down the line. Now we want to find some measure similar to sort of the average of our deviations. The problem is that if we added these all up, they'd add up to 0. And so we need to do something else, and there's a couple approaches that we could use. It turns out the one that makes the most sense is to square the deviations. There's various reasons for this, but most simply, it will definitely make the values positive. So -5 squared is 25, 25, 25, 25, 25, 25, 25, 25, and in this particular case, it's very easy to calculate, too. And so we find all of our deviations there. So now we're going to find the sum of those squared deviations. So we're going to add all these up. Let's see here, I'm adding up 25 10 times, right? So that ends up being 250. So we're going to find the sum of the squared deviations. Actually, I'm going to write that down here, 250. And then I'm going to divide it by not how many, not by how many, okay. Well, what we divide by depends upon whether our data was coming from a sample, in other words, from a sampling of all of the data, or whether it was representing the whole population. So if it's the population, then we divide by n, the number of data. If it's the sample, then we divide by n minus 1, 1 less than the total number of data. In this case, this is representing the entire section's scores, and so we're going to divide by n. We're going to divide by n. We're going to divide by the 10 scores, and we're going to get 25. Now, at this point, we have something called variance, or more specifically, the population variance, since this was for the entire population. The standard deviation is the square root of the variance, so it's the square root of 25. The square root of 25 is 5, and so the standard deviation of this data set is 5 units. Now, for comparison, let's look at all of our other data scores. When all of our scores are the same, the deviation is going to be 0. The data set we just looked at had a deviation of 5. In this case, all the scores are much closer to the mean, and so the standard deviation is going to be smaller. In this case, even though we had the same mean and median and range as our data set B, the standard deviation here is much smaller because most of the data is very close to the mean, and we only have a few values that are further out. So if the data is very spread out, we have a big standard deviation. If the data is closer together, we have a small standard deviation. So we have 8 male students' weights in pounds recorded here, and we're going to find the standard deviations of these weights. And just to be clear, this data was a sampling, and so we're going to use the sample standard deviation here. So the first thing we need to do is find the mean of our data. And so to do that, we'll go ahead and just add up all of our data. So we add up all of our data here, which adds up to 1,400, and divide it by the number of data values. We got 8 data values, and we end up with a mean of 175. So now we can take each value and find our deviation from the mean. So for the weight of 165, the deviation would be, that's not the right number, it should be the mean. Minus 175 is negative 10 is our deviation there. For 145, we got 145 minus 175 is negative 30. For 160, we got negative 15, and so on for the rest of the values. So now that we have all the deviations calculated, now we can go and find our squared deviations. So we're going to do that by squaring each of these values. So negative 10 squared is 100. Negative 30 squared is 900. 15 squared is 225. 25 squared is 625. Sorry, negative 25 squared, but when we square it, it becomes negative. It becomes positive. 5 squared is 25. 45 squared is 2045. 25 squared is 625, and 5 squared is 25. And now we'll go ahead and add all those up, and the sum of all of our deviations is 4550. So remember that standard deviation is found by finding the sum of the squared deviations and then dividing by either n or n minus 1. N if it's from the population, or n minus 1 if it's from the sample. So we're going to take our sum of squared deviations here, And because this is from a sample, we're going to divide by n minus 1. So we're going to take our 4550 and divide it by 7, which is 1 less than our number of data, which was 8 pieces of data. So we go ahead and divide that, and we end up with 650. Again, that's what we call variance. And then our standard deviation will be the square root of that variance. So the square root of 650 is about 25.5. It's actually like 25.4951, but again, typically we round to one more decimal place than our original data had. And so our standard deviation is 25.5 pounds. Standard deviation is measured in the same units as the original data. So there is the standard deviation. So we have a set of females' heights, and it's been sorted from smallest to largest, and we want to find the 5-number summary. Now, the 5-number summary is based on the median, kind of like the standard deviation was based on the mean. So this is a measure of spread based on the median, and the idea is that we're going to take all of our data. So suppose we have this big chunk of data, and we're going to divide it up into quarters. So we're going to divide our data into 4 chunks. And the median, remember, divides the data in half, right? And so the median will be in the middle. At the bottom, we'll have a minimum value, and at the top, we'll have a maximum value. Now, these two values are called the quartiles. This one is called quartile 1, or Q1, and this is called quartile 3, or Q3. You might be able to guess that Q2 is the median. So quartile 2 is the median. So we need to divide our data up into quarters. By the way, in some other situations, you'll hear quintiles, and quintiles divide the data up into chunks of 5 rather than quarters. So we're going to go ahead and see if we can find these. So minimum and maximum are pretty easy, right? Our minimum is here, our maximum is here, and our median, when we have 9 pieces of data, will be, let's see, it's odd, and so it's going to be the 5th piece of data, and so my median is here. So the main thing we need to find now is the quartiles. And so to do that, we're going to use something called the locator method. So we're going to calculate a locator. Now, remember that the quartiles are supposed to divide the data into quarters. And so we're going to figure out where is 1/4, or in other words, 25% of the data values. So in this particular case, 0.25 times 9, let's see here, 0.25 times 9 is 2.25. Now, if this comes out to be a decimal value like it does here, so if this is a decimal, then that means that the quartile value is going to be a single number. So then we go up to the next whole number, and we use that data value. So in this case, we're going to take this and we're going to go up to 3. Notice we're not rounding here. We're moving up to the nearest to the next whole value. And so the third data value is going to be our quartile 1. And so quartile 1 is going to be right here. It's our third data value. Now to find that's our first quartile. Our third quartile, we do almost the same thing, but we use 75% rather than 25% because the third quartile is 75%, 75% of the data is lower than it. So in this case, that comes out to 6.75, and we follow the same rule. If it's decimal, we're going to go up to the next value, and so this would be the 7th data value. And so the 7th data value here is 5, 6, 7, this one, and that's our quartile 3. So to answer our original question here of find the 5-number summary, the 5-number summary here is those 5 numbers. The minimum, the quartile 1, the median, the quartile 3, and the maximum. That's our 5-number summary. So in the next video, we'll look at what to do if this locator does not come out to be a decimal. So in this example, we calculated a 5-number summary, and when we were using the locator method to find our quartiles, we looked at the case where the locator comes out to be a decimal value. In that case, we went up to the nearest whole value and used that data value. So now suppose that we had only 8 pieces of data. So the minimum and the maximum are still very easy to find. The median now, remember, if it comes out to be a whole number, then we're going to find the mean of the 4th and 5th data values, which is going to be 65, so that's our median. And now let's see if we can find our quartiles. So we're going to do the same thing. We're going to use the locator method, which means we're going to find where 25% of our data is, or for quartile 3, we'll do 75%. So here, if we do 25, that's not a 5. If we do 25% of our 8 pieces of data, we come up with 4, which is not a decimal value. So if this is not decimal, then we're going to basically run into the same thing we did with our median, where we're going to then find the mean of the Lth and L plus first data values, which is a fancy way of saying, like if we come up with 4 here, then we're going to use the 4th and 5th. So this value is going to give me the first one to use, and then we also use the next one in the list. And wow, I did not calculate that right. I'm sorry. 25% of 8 is 2, not 4. And so we're going to use the, let me correct that there. We're going to use the 2nd and 3rd data values. So if the 2nd and 3rd data values are here and here, so we're going to find the mean. Just to clarify, we're going to find the mean of the 2nd and 3rd data values. So the mean of 60 and 61, add them up, divide by 2, of 60 and 62 is 61. For quartile 3, we'll do the same thing. We'll use the locator method. So we'll use 75% of n of our data value, and that comes out to be 6. Again, that is a whole number. It's not a decimal. And so we're going to need to use the mean of the 6th and next one, 7th data values. So let's see here, 1, 2, 3, 4, 5, 6, and 7. So 6th and 7th data values, we'll find the mean of those is 68. So our 5-number summary here would be 59, that's the minimum. 61 is quartile 1, 65 is the median, 68 is quartile 3, and 70 is the maximum. And that's the 5-number summary for that data. So let's go back to our quiz score data and see if we can find the 5-number summary for each of these. Now, each of these data sets has 10 pieces of data, and so using our locator method with 10 pieces of data, that's 2.5. That is a decimal, and so we're going to use the 3rd data value, for our quartile 1. Likewise, for quartile 3, let's see here, that's going to be the 8th data value is going to be our quartile 3. So let's see here, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 8, 3, 8, 3, 8. And so those are all of our quartile 1 and quartile 3 values. Now notice for our median, 10 over 2 is 5. That is a whole number, so between 5th and 6th. So we need to find the mean of the 5th and 6th values in order to find our median. So let's hear 1, 2, 3, 4, 5. Halfway between is 5. 1, 2, 3, 4, 5. Halfway between is 5. 1, 2, 3, 4, 5. Halfway between is 5. 1, 2, 3, 4, 5. Halfway between is 5. And actually, I think we already knew that, but oh well. And then, of course, we have our minimum and our maximums for each of these data sets. And now we can write our 5-number summaries. So for this data set, it is 5, 5, 5, 5, 5. They're all 5, right? Why? Because all the data is 5. Our next set is 0, 0, 5, 10, 10, which gives us a really good idea that 25% of the data is between 0 and 0. And 25% of the data is between 10 and 10, right? So we got a good idea that there's a lot of 10s here and a lot of 0s here. The middle 50% of the data, right, 25% is between 0 and 5. It's not obvious that those values are all 0, but we still get a better idea than we did from just the median or just the range of values. For this set, let's see here, 4, 4, 5, 6, 6. Gives us a good idea that this data is all fairly closely lumped. And here we've got 0, 5, 5, 5, 10. And you can definitely tell a difference here between the scores in section B and section D now, where here we can see that 50% of the class, at least 50% of the class, got scores of 5, right? Because this is a quarter of the data, and then this is a quarter of the data. Whereas here, the scores were definitely further out towards the ends. And so this helps reveal the spread of the data in a fairly small, concise way. Now, of course, with only 10 pieces of data, doing a 5-number summary is awfully silly. But if we had several hundred pieces of data here, the 5-number summary would definitely provide a nice, condensed way of looking at the data. So here we have our income data again, and we want to create a 5-number summary for this data. And so we need to figure out where our quartile 1, quartile 3, median, and min and max are. So minimum is fairly easy, right? That's our smallest value, and our maximum is fairly easy. That's the largest value. And now we need to find our quartile 1, quartile 3, and median. So for quartile 1, our locator will be 25% of our data. We have 100 pieces of data is 25. And since that's a whole number, we know we need to go between the 25th and 26th data values. So the mean of the 25th and 26th data values. For our median, and I think we've done this one before, but that's okay. For our median, right, we find half of our data values. Notice it's really the same as multiplying by 0.5 there. We come up with 50, which is a whole number, so we need the mean of the 50th and 51st data values. And then for quartile 3, let's see, it's going to come out to be 75, and so we need the mean of the 75th and 76th data values. Okay, so now we got to get counting. So here we have 6 pieces of data. Plus another 8 is 14, so together this is 14 pieces of data. Plus 11 is 25, and so here we've got 25 pieces of data. And then let's see, if we go down plus another 17, let's see, 17 and 25 is 42, so that's 42 pieces of data. And so notice now we've passed our 25th and 26th pieces of data. In this case, the 25th piece of data would have been here, right? Because that was, these added up to 25 pieces of data. So the 25th piece of data is 25,000. whereas the 26th piece of data is in the next category here, is 30,000. And if we find the mean of those, so if we add those up and divide by 2, we will get, let's see, what is that, 27.5 thousand as our quartile 1 value. So let's continue on here. So if we continue counting, let's see, if we go 42 plus our 19 there, gets us up to 61. So we have 61 pieces of data here. So that means that data values 50 and 51 both fell in the 35,000 category. So the mean of those is 35,000. And now, let's see here, 61 and 20 is 81. So we have 81 pieces of data if we go all the way down to here, which means the 75th and 76th pieces of data must have been in this category, in the 40,000 category. So 40,000 and 40,000. And if we find the mean of those, of course, we're going to get 40,000. And so it looks like our quartile 3 value is 40,000. So let's go ahead and write our five-number summary now. Our minimum is 15,000. Our quartile 1 value was 27.5 thousand. Our our median was 35,000. Quartile 3 was 40,000, and our maximum was 50,000. And so there is the 5-number summary for this income data. So when we create a 5-number summary, it can be useful to create a graphical representation of that information. And so earlier we calculated that from a set of female heights, we had a 5-number summary that looked like this. And we're going to create something called a box plot. So a box plot is, again, a graphical representation of the 5-number summary. So we're going to start by creating a number line. Now this should be a honest-to-God number line, evenly spaced. It needs to range from 59 up to 72. And so I'm going to go ahead and start it at 55, just for simplicity's sake. And let's see here, 56, 7, 8, 9, 60. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And so there is my number line, which is going to let me show my heights, which are measured in inches. And now we're going to construct our box plot. So the idea is at each of these values, I'm going to draw a vertical line. So I'm going to draw a vertical line at 59, at 62, at 66, and at 69, and at 72. Okay? Now I'm going to create a box ranging from quartile 1 to quartile 3. So starting here at 62, up to 69, with 66 in the middle. You don't necessarily have to label those values, but can come in handy. So this is why it's called a box plot, is because it has this box in the middle of it. And then we extend lines out from the box to the minimum and the maximum. Sometimes this is called a box and whiskers plot, because we have a box and then we have these sort of whiskers coming out on either side. In this case, going down to 59 and 72. Now, there are different types of box plots that are out there. Sometimes they won't actually extend all the way to the maximum or minimum, but in the type that we're going to look at, they do. And so there is our box plot. By the way, sometimes this here is called the interquartile range, the values that are contained within the box there. But that's not too important. Let's create one more. So here was the data from our income data, and let's create a box plot here. So once again, we're going to create a number line. Needs to range up to 50 from 15. So maybe I'll start here at 15, and maybe I'll just create every 5 here. So 15, 20, 25, 30. So 20, 25, 30, 35, 40, 45, 50. That should work. So there is our number line, and these are going to be incomes. And so we are going to, and I'm going to do a slightly different approach this time. I'm going to draw a box from my quartile 1 to my quartile 3. So there's my quartile 3. Quartile 1 is here, halfway between 25 and 30. And there's a box representing my, from quartile 1 to quartile 3. And now I'm going to draw in a line at the median, and then extend my whiskers out to the maximum and down to the minimum. And there is a box plot for our income data 5-number summary. So box plots can be particularly helpful when trying to compare two different data sets. So in this case, we have two different fast food restaurants, two different stores, and let's see what we can deduce from these box plots. So first thing we might look at is the median, and remember the score at the middle bar there is the median. And so store 2 has a smaller median, which means that remember, the median represents the score that divides the data in half, and so 50% of the time you're served in under 2.3 minutes here, and 50% of the time you're served in under 2.1 minutes there. So one could argue that on some measure of average, remember average is a not specific term, but by some measure of average, store 2 seems to serve a little bit faster. However, we also can notice that this range of values, because remember this represents 50% of the data as well, because these quartiles are dividing the data up into quarters. So 50% of the time here, you're served between 1.8 and 2.9 minutes. Here, 50% of the time, you're served between 1.1 and 5.7 minutes. And so the second store is a lot less consistent in the time, and we can also see that in this very large range. The first store seems to be more consistent in its delivery. In fact, 75% of people are served within 2.9 minutes. Only these unlucky 25% here were served in a longer time. So if you're feeling really lucky, you might try store 2, because you might get lucky and get served really quickly, faster than you might in store 1. But certainly if you just can't spare a large amount of time, then store 1 might still be your better bet, since they seem to be a little more consistent in serving quickly. So let's look at another case. So the box plot here shows the birth weight of infants with severe idiopathic respiratory distress syndrome, or SIRS. The box plot is separated to show the birth weight of infants who survived versus those that did not. And so what can we deduce from this, from these box plots? So we can tell that the birth weights of infants that died appears overall to be smaller than the birth weight of the infants that survived. In fact, we can see that the median birth weight of those that survived is about the same as the quartile 3 of birth weight of those that died. So this means that, for example, here, this is 25% of infants that survived. 25% of infants that survived were heavier than all of the infants that died. Likewise, notice that the quartile 1 here is bigger than the median here. Remember, quartile 1, this is 25% of the data, this is 75% of the data, so 75% of infants who survived had a higher birth weight than the median birth weight of an infant that died. So this gives us a quick, admittedly informal way to look at data and get some idea what's going on.